Now, the next point is, I've already told you, which is delta of t is equal to d by dt of u of t means the impulse signal is the derivative of the step signal. Similarly, in the same fashion, delta of t response is h of t, u of t response is s of t. So in the same fashion, we are also going to follow the same relation, which is h of t is equal to d by dt of s of t. So always remember, here, you can see clearly from this picture, delta of t is a derivative of this unit step signal. So in the same fashion, their response is also going to follow the same relation, which is for delta of the response is h of t, and for u of the response is s of t. So they are also going to follow the same relation. Suppose if the inverse is also true, which is u of t is the integration of the step signal, the integration of the impulse signal, right? So impulse signal. So here, small correction here. This small simplify to t. Let me write here. This is t. See, in the same fashion, u of t response is s of t. So s of t is called integration from minus into t h of t dt. So this is also going to follow the same relation. So whatever the inputs are going to follow the relation, same thing the response is also going to follow the same relation. So now the next point is, I already told you the x by r ratio. The listen carefully. I am going to write the x by r ratio of the induction motor is always greater than the x by r ratio of the servo motor. So these things I already told you. Then what is the reverse? Reverse is nothing but r by x ratio of the induction motor will be lesser than the r by x ratio of the servo motor. So you can write in another function also, which is the r by x of the servo motor is greater than the r by x of the induction motor also you can write. But this is the thing I already told you. The x by r ratio of the induction motor is always greater than the x by r ratio of the servo motor. So if you do the reciprocal, then what is going to happen? The r by x ratio of the induction motor is always lesser than the r by x ratio of the servo motor. You can also write in the other function, which is r by x ratio of the servo motor is greater than the r by x ratio of the normal induction motor. So always you have to remember, which is the x by r ratio of the induction motor is always greater than the x by r ratio of the servo motor, because I have already told you for induction motor the size is greater. Here for servo motor the size is lesser. Shortcut to remember. Therefore we can say the x by r ratio of the induction motor is always greater than the x by r ratio of the servo motor. So if you write in the reciprocal, then we are going to get the r by x ratio of the induction motor is always lesser than the r by x ratio of the servo motor. You can write in the other fashion, which is the r by x ratio of the servo motor is always greater than the r by x ratio of the normal induction motor. So now the next point is, after drawing the root locus, the closed loop poles corresponding to a specific value of the gain k can be determined by using the Navier criteria alone. So after drawing the root locus, the closed loop poles corresponding to a specified value of a gain k can be determined by using the Navier criteria alone. I have already told you. See, basically we have two conditions. One is the angle criteria and the magnitude criteria. See, angle criteria alone is sufficient to tell whether a point is lying in the root locus or not. For example, with the help of magnitude criteria, suppose a root locus graph is drawn. Then, for a particular value of the closed loop poles, what is the value of k and k, then we can figure out only with the help of magnitude criteria alone. So therefore, we can say, after drawing the root locus, the closed loop poles corresponding to a specified value of the gain k can be determined by using the magnitude criteria alone. The next point is, the angle criteria determines whether a given point on the S-plane lies on the root locus or not. I already told you. Whereas the angle criteria determines whether a given point is going to lie on the S-plane of whether a given point on the S-plane lying on the root locus or not. So if any point is going to satisfy the angle criteria, we can say that point is lying on the root locus. Otherwise, it is not going to lie on the root locus. So these things always you have to keep in your mind. The next point is, by increasing the system gain, steady state error in the system can be reduced. So this relation always you have to keep in your mind, which is the steady state error is always directly proportional to 1 by k. 1 by k. As the gain k increases, the steady state error will decrease. As the gain k increases, the steady state error will decrease. By increasing the system gain, steady state error in a system can be reduced. As the gain k increases, the steady state error will decrease. As you can see clearly from this equation, As the gain K increases, the steady state error will decrease. Steady state error is always equal to proportional to 1 by K. As the gain K increases, the steady state error will decrease. And also, I already told you one more thing also. Theta is directly proportional to 1 by root K. And also, theta is directly proportional to 1 by P cos also I already told you. These relations always you have to keep in your mind because these are very much useful for competitive examinations. So we can say by increasing the system gain, steady state error in a system can be reduced. So by increasing the system gain, steady state error in a system can be reduced. So therefore, in simple words, I can say as the gain increases, the steady state error decreases, the damping ratio decreases, the peak also increases. So these things you can see clearly from this relation. The next point is phase margin is the amount of angle to make the system unstable. Phase margin is the amount of angle to make the system unstable. So listen carefully. What is the meaning of phase margin? Phase margin, suppose if you are going to get some angle on 30 degrees, suppose if you got 100 degree, this much angle is there, up to this much angle the system is stable. But if you are exiting this angle, means the system will become unstable. Listen carefully. Up to this angle, the system will be stable. But if you exceed more than this, the system will be unstable. So this is the meaning of phase margin. Phase margin is the amount of angle to make the system unstable. So up to this much amount of angle, the system will be stable. But if you exceed more than this, the system will be unstable. Phase margin is the amount of angle to make the system unstable. Phase margin is the amount of angle to make the system unstable. So therefore we can say up to this angle, the system will be stable. But if you exceed more than this, the system will be unstable. So this point always you have to keep in your mind. The next point is, in order to make the steady state error to 0 in a negative feedback control system, we always prefer the integral control. In order to make the steady state error to 0 in the case of negative feedback control system, we always prefer the integral control. I already told you, whenever you are going to use the integral control, means 1 by s terms you are going to get. So the steady state error is going to get decreased because it is nothing but lag compensator. I already told you, lead compensator is basically used to improve the transient response, whereas the lag compensator is basically used to improve the steady state response. So this is nothing but PD. This is a PD controller and this is a PA controller. As you can see clearly from this relation. So here B is there, here also B is there. Here lead has more votes, so transit has more votes. Lag has less votes, steady has less votes. Similarly, this is used for PA. So therefore we can say that lead compensator is always used to improve the transient response, means is going to decrease the rise time, so bandwidth will increase. And it is basically a PD controller. Similarly, in the case of lag compensator is basically used to improve the steady state response. With the steady state, it will decrease. It is nothing but a PA controller. So therefore, if you use an integral controller, the steady state will decrease in the case of the negative feedback system. The next point is, a differentiator is not usually used in a control system because it is going to increase the input loss. So differentiator is not usually used in the case of control system because it is going to increase the input loss. I already told you. Suppose if the input is now, you can say 0.2 into sine of 100,000 t, I put it like this input. Then what is the output we are going to get? If you give this to the differentiator circuit, then we are going to get basically 2 into sine between this cos of 1000 t we are going to get. So you can say the input differentiation we are going to get output in this fashion. So you can say output is now having a lot of magnitude. Suppose input loss is a very very small magnitude, the high frequency, and output we are going to get a huge magnitude with the same amount of frequency. So therefore you can see the noise is get amplified with the help of differentiator. That is the reason a differentiator is not used in the case of control system because this is going to increase the input noise or it is going to amplify the input noise. So this is the reason we are not going to use the differentiator in the control system, because if you are going to use a differentiator in a control system, the input noise is going to get amplified, or we can say the input noise is going to get increases. That is the reason we are not going to use the differentiator in the case of control system. So if you use a differentiator in the control system, the input noise is going to get amplified, or it is going to increase the input loss. So this is the basic reason for not using the differentiator in a control system. So finally I can say a differentiator is not usually used in the case of control system because it is going to increase the input loss. The next point is if the stability error for step input and the speed of response be the criteria for design, then PID controller is preferred. If the steady state error for step input and the speed of the response, a small correction here, steady state error, and not stability error. So a small correction here, it is a steady state error, steady state error. If the steady state error for step input and the speed of the response for design, the PID controller is preferred. I have already told you so many number of times. In the case of PID controller, what is going to happen? PID is nothing but lead compositor is going to decrease the rise time, so the bandwidth is going to get increased. And the steady state is going to get increased. Error is going to get increased here. In the case of PI controller, this lag compositor, it is going to decrease the steady state error. So therefore, here rise time will increase. So bandwidth will decrease. Similarly, in the case of PID, both the transient response and the size response both are going to get increased. So the rise time is going to get decreased and the steady state is also going to get decreased. So now bandwidth will increase. So you can see, if you want to have a least steady state error, if you want to have a least transient time, no speed of response, then we have to use the PID controller. So if the steady state error for the step input and the speed of response be the criteria, then for design, then we have to use the PID controller preferred. So always remember, in the case of lead capacitor, it is basically nothing but the PID controller. In this, we are going to increase the speed of the response, means the rise time will decrease, so bandwidth will increase, but it will affect the steady state error. So it will increase the steady state error. Means if it is improving the transient response, it will decrease the steady state. If it is improving the steady state, it will decrease the transient response. So in the case of PI, it is going to improve the steady state response, the steady state will decrease. So it is going to decrease the transient response, the rise time will increase, so bandwidth will decrease. Whereas in the case of PID, it improves both the rise time as well, it improves both the transient response as well as steady state response. So transient response, the rise time will decrease, and the steady state is also going to get, error is also going to get decreased. So as the rise time decreases, the bandwidth will increase because the rise time and the bandwidth is always equal to constant. So this point always you have to keep in your mind. The next point is the state space model representation is instead of P is equal to A into X of t plus B into U of t, Y of t is equal to C into X of t plus D into U of t. Suppose these constants A, B, C, D are also with respect to time, then it is going to represent the continuous time varying system because everything is in terms of time and this A, B, C, D also are also varying with time, so we can say it is a time varying system. Suppose if all these are time, like variables x are with respect to time, u with respect to time, and y with respect to time, then we can say by the ABCD constants means we can say it is going to represent the continuous time invariant system because ABCD are constant with respect to time. But if ABCD are also varying with time, then we can say it's a time varying system. So always remember, we can say, let me write here, here x dot of t is equal to A into X of t plus B into U of t. Y of t is equal to C into X of t plus D into U of t. See, basically this is our state space model representation. Here A, B, C, D are also with respect to time. Then we can say this is called as the continuous time invariant system. But here A, B, C, D also vary with respect to time. So we can say it's a continuous time invariant system. So this is called as a continuous time invariant system, and this is called as a continuous time varying system. So these things always you have to keep in your mind. So this is called the continuous time invariant system, and this is the continuous time varying system. The next point are the true facts are. Some true facts now we are going to discuss, which are the state model of the system is not unique. Yes, the state model of the system is not a unique one. Yes, I already told you. In transfer function model, initial conditions are taken as 0. Transfer function is applicable only for linear time invariant systems, LTI systems only. In state space model, initial conditions are taken into account. So listen carefully. Let me tell you the difference between the transfer function model and the state space model. In the case of transfer function model, initial conditions are assumed as 0. Whereas this transfer function model is applicable only for the LTI systems, linear time invariant systems only. Whereas in the case of state model, here the initial conditions are taken into consideration, means they are not taken as 0, they are considered. And also, we can say it is applicable for both LTI systems as well as the non-LTI systems also. Both the LTI as well as the non-LTI systems also is applicable. And the system model is not a unique one. Whereas the transfer function is a unique model. So these things always you have to keep in your mind. So let me tell you the difference between the transfer function model as well as the state space model. In the case of transfer function model, the initial conditions are taken as 0. Whereas in the case of state space model, initial conditions are taken into consideration. Whereas in the case of transfer function model, we can say it is applicable for only LTI systems. Whereas the state space model is applicable for both LTI as well as the non-LTI systems also. Whereas the transfer function is always a unique one, whereas a state model is not a unique one. For a given system, it is not a unique. So finally, I can tell you the difference between the transfer function model as well as the state space model, which is, I can say like this, which is in the case of transfer function model, initial conditions are taken as 0. Whereas in the case of state space model, initial conditions are taken into consideration. Whereas in the case of transfer function model, it is applicable for only LTI systems, linear time invariant systems. Whereas the state space model, it is applicable for both LTI as well as the non-LTI systems also. Whereas in the case of transfer function model, you can say that it is a unique one. For a given system, it is a unique. Whereas a state space model, for a given system, it is not a unique one. So these things always you have to keep in mind. The next point is, by using lead compensator, the rise time is decreased, so speed of the response is increased. So I already told you, lead compensator is always used to improve the transient response. Improving the transient response means the rise time will decrease, so bandwidth will increase. As the rise time decreases, the speed of the response will increase. So the response will increase. So therefore, we can say that by using lead compensator, the transient response is going to get improved. Means the rise time will decrease, so bandwidth will increase. Rise time decreases, means the speed of the response will increase. The next point is, state variables can be taken as current passing through an inductor, voltage across the capacitor, as well as the output of the indicator. So these are considered as the state variables. Means the current passing through the inductor, the voltage across the capacitor, and the output of the integrator. So basically, listen carefully. Current through an inductor, what is the expression of the current through an inductor? So you know V is equal to L divided by dt. And what is the value of I? I is equal to 1 by L, integration of V dt. So this is the expression of the current in an inductor. And what is the voltage current relationship across the capacitor, which is I is equal to C dV by dt. Then what is the value of V? V is equal to 1 by C integration of I dt. Similarly, for an integrator, what is the output expression? Output is equal to integration of the input. So we can see, if any variable, integration of other variable, then this is called as the state variable. So current in an inductor is considered as a state variable. Voltage across the capacitor is considered as a state variable, and the output across the output of the integrator is also considered as the state variable, because these are the integration of some other variables. So these are called as the state variables. If any parameter is the integration of other parameter, then that parameter is called as the state variables. So you can see the current in an inductor is called as the state variable. The voltage of the capacitor is considered as the state variable, and the output of the integrator is also considered as the state variable, because these are integration of some other variables. So therefore we can say these are called as the state variables, because they will have some initial conditions also, because we are going from integration from minus infinity to t. So we are going from minus infinity to t. So based on this, we can say that it will have some initial conditions also, which is minus into 0 plus 0 to t. We are going to split this integration it will become as into 0 plus 0 to t. So because of this, it will some initial conditions are there. Therefore, we can say that the current in an inductor, current passing through an inductor, and voltage across the capacitor, and the output across the output of the integrator. These are considered as the state variables because they have some initial conditions are associated with these variables. So because of this only, we can say these are called as state variables because some initial conditions are associated with these variables. So therefore, we can say these are called as state variables. So finally, I can say state variables can be taken as current passing through an inductor, voltage across the capacitor, and output of the integrator. The next point is a rough measure of the bandwidth of a system is given by gain crossover frequency. So, see, bandwidth is nearly equal to gain crossover frequency. So this is the rough approximation, but not the exact one. A rough measure of the bandwidth of a system is given by the gain crossover frequency. So we are going to assume it is not exactly equation, but it's an approximate equation. So bandwidth is nearly equal to gain crossover frequency. It is a rough measurement, or we can say rough approximation, but not the exact one. So we can say a rough measure or the rough approximation of the bandwidth of a system is given by the gain crossover frequency. So we can say a rough measure of the bandwidth or the rough approximation of the bandwidth of a system is given by the gain crossover frequency. Gain crossover frequency means it is a frequency at which the amount of the open loop transfer function is equal to 1. So it is a frequency at which the amount of the open loop transfer function is equal to 1. So we can say the bandwidth is approximated or rough approximated to gain crossover frequency. With the help of this, we are going to get the bandwidth of a corresponding system. It is a rough expression or rough measurement, but not the exact one. So gain crossover frequency means it is a frequency at which the bandwidth of the open loop transfer function is equal to 1. So this point always you have to keep in your mind. The next point is the principle of argument is the basis for the Nyquist criteria. So the principle of argument is the basis for the Nyquist criteria. So I have already told you the Nyquist criteria. So principle of argument is the basis for the Nyquist criteria. So we can say that the principle of argument is the basis for the Nyquist criterion. So we can say the principle of argument is the basis for the Nyquist criterion. So we can say the principle of argument is the basis for the Nyquist criterion. The principle of argument is the basis for the Nyquist criterion. The next point is the transfer function has a second order denominator and a constant gain in a numerator. The system has two zeros at infinity. See, I have already told you one important point. Always, number of zeros should be always equal to number of poles. So in this question, the given transfer function is a ratio of numerator over diameter. Numerator is a constant and denominator is a of second order. Means the number of poles are 2. So definitely, the two zeros should be always at the infinity. So always remember, number of poles should be always equal to number of zeros. Suppose, let me take some example. Suppose if there are 3 poles, then I have only 2 zeros. Then one of the root locus branch is going to terminate at a 0 which is present at the infinity. So always remember, number of poles should be always equal to number of zeros. In respect of the transfer function, always number of poles should be always equal to number of zeros. So in this case, there are 2 poles. So the remaining 2 zeros will be present at infinity. So there are 2 zeros which are going to present at the infinity. So always remember, number of poles will be always equal to number of zeros. So sometimes some zeros can be present at a finite values, but some zeros can be present at the infinite values. So this is the point always you have to keep in mind. So this point always you have to keep in mind, which is number of poles will be always equal to number of zeros. Number of poles will be always equal to number of zeros. Sometimes some zeros can be at finite position, whereas the remaining zeros can be present at the infinite position. But overall, number of poles will be always equal to number of zeros. The next point is that for continuous oscillations means what is the meaning of zeta? Zeta is equal to 0. When zeta is equal to 0, we say undamped case means undamped means also will be present for all the time. So when zeta is equal to 0 means undamped case. Then what is the value of theta? So you know theta is equal to cos inverse zeta. As zeta is equal to 0, so cos theta is equal to 0. So therefore theta is equal to 90 degree. So C of t, expression of response C of t, when the input is u of t, what is the C of t expression? I've already told you, 1 minus e to the power of minus zeta omega and t by under root over 1 minus zeta square, sine of omega t plus theta. I've already told you, whereas omega t is called omega n into under root over 1 minus theta square, and theta is equal to, what is the expression of theta? Theta is equal to cos inverse of zeta, cos inverse of zeta. So here theta is equal to 0, so cos phi is equal to 0, so theta is equal to 90 degree. So here, as theta is equal to 0, so omega d is equal to omega n. If you substitute theta is equal to 0, this value you are going to get 1, and this value also you are going to get 1. So 1 minus sine of omega n t plus 90. So sine into theta is equal to cos theta. Here you are going to get 1 minus cos of, here theta is nothing but this one, omega d t, omega d t, omega d is nothing but omega n t, omega n t. Omega n is nothing but 2 pi f1, 2 pi f1. So this is the output that we are going to get. So therefore we can say this is the expression of the output for unit step input for the second order system, which is C of t is equal to 1 minus e to the power of minus zeta omega n t by under root over 1 minus zeta square, sine of omega d t plus theta. The theta is equal to cos inverse of zeta, and omega d is equal to omega n into under root over 1 minus zeta square. So if you want to have a continuous oscillation, zeta is equal to 0, so if you substitute theta is equal to 0, you are going to get this expression. In place of omega n, if you substitute 2 pi fn, we are going to get this equation. So now the next point is, for two-phase AC servo motor, if the rotor's resistance and reactance are respectively R and X, its length and diameter are respectively L and D, then what is the meaning of this one? X-Y ratio is small, whereas the L by D is large. So D is the diameter. Listen carefully to this concept. For two-phase AC servo motor, with the rotor resistance and the reactance are respectively R and X, its length and diameter are respectively L and D. So basically, in the case of AC servo motor, here diameter is very small, but the length is very large. I've already told you this important point. So diameter is very less, but the length is very large. So we can say L is greater than D. So L by D is always greater than 1. So we can say L by D is nothing but it is a large case. Whereas XYR is a small for servo motor. I've already told you it's a very small for a servo motor, two-phase servo motor. So therefore we can say XYR is small, whereas L by D is large. So this is the case for the two-phase AC servo motor. So we can say for two-phase AC servo motor, if the rotor resistance is R and the rotor reactance is X and its length is L and its diameter is D, then we can say in the case of AC servo motor, two-phase servo motor, so this is the rotor construction, less diameter but large length. So L is always greater than D. So L by D is always greater than 1. So we can say L by D is large, because X by R is very small. So therefore this is the case. The next point is, only closed loop system have tendency to oscillate. As I already told you, only closed loop system have a tendency to oscillate. So only closed loop systems have the tendency to oscillate. What is the meaning of this one? Basically you can see, in the case of closed loop systems, the response you can see oscillation. Only in the case of closed loop systems only you can see the oscillations in the output, but not in the case of open loop systems. So therefore we can say you can see the oscillations only in the case of closed loop systems. Only closed loop systems have the tendency to oscillate. So only closed loop systems have the tendency to oscillate. So we can say only closed loop systems have the tendency to oscillate. So only closed loop systems have the tendency to oscillate, but not the open loop system. So therefore we can say only closed loop systems have the tendency to oscillate. So therefore we can say only closed loop systems have the tendency to oscillate. So only closed loop systems have the tendency to oscillate. The next point is, for making unstable systems to stable, gain of the system should be decreased. I've already told you one important point. What is that point here? We can say, I've already told you two important points. We can say, see, the steady state error is inversely proportional to K, and Zeta is inversely proportional to under root over K, and MP is inversely proportional to zeta. So these points are already told you so the number of times. See, as the k value increases, the steady state area decreases, zeta decreases, MP increases. So this one I've already told you. See, whenever the value of k increases, the root one is going to shift to as of S plane, the system will become unstable. This one I've already told you. So therefore, as the gain k increases, the system will become unstable. So if it decreases the gain k, the stability will increase. For making unstable system to stable, gain of the system should be decreased. I already told you, if you want to make any system to become stable, first thing is you need to decrease the gain of the system, and also you need to add the zeros in order to make the system stable. So therefore we can say, for making unstable system to stable, gain of the system should be decreased, or we even have to add the zeros in order to make the unstable system to stable system. So therefore we can say, for making unstable system to stable, gain of the system should be decreased. Gain of the system should be decreased, or you can add the zeros in order to make the unstable system to stable. Then next point is, number of closed loop poles in the right of S plane can be determined using the Nyquist criteria. So I already told you what is the Nyquist criteria. N is equal to P minus Z. So here, listen carefully. Here N is nothing but number of encirclements in the G of S, H of S plane at -1, J0. So anti-clockwise means take positive, clockwise means takes negative. What is the P? P is nothing but the number of poles of G of S, H of S which are in the RHS of S plane, and Z is nothing but number of closed loop poles of particular G of S, H of S which are in the RHS of S plane. Listen carefully. N is equal to P minus Z. So here N is a number of encirclements which are occurred at -1, 0 in the G of S, H of S plane, in the G of S, H of S plane at -1, 0. Anti-clockwise take it positive, clockwise take it negative. Here P is nothing but number of poles of G of S, H of S which are present in the RHS of S plane. Z means the number of closed loop poles of one place G of S, H of S which are in the RHS of S plane. So if you know this one, from this we are going to get the value of Z. So if you know N, if you know P, we can get the value of Z. If Z is equal to 0, we can say no closed loop poles are going to lie in the RHS of S plane, so system is said to be stable. Therefore, we can say the number of closed loop poles in the RHS of S plane, which is Z, which can be determined with the help of Nyquist criteria. So if you know N, if you know P, we can get the value of Z. So Z is nothing but number of closed loop poles which are present in the RHS of the S plane. Closed loop pole means the roots of characteristic equation, which is 1 plus G of S, H of S. The next point is, Bode analysis uses two plots, one for the magnitude and the other for the phase angle. So Bode analysis is basically it is going to use the two plots. One is for the magnitude and the other is for the phase angle. Magnitude means always we are going to take the magnitude in terms of the dB. So what is the magnitude part? 20 log of G of S, H of S with a base 10 versus log omega, and the phase angle is the phase angle of G of S, H of S versus log omega. So this above one is called as this one is called as the magnitude plot, and this is called as the phase angle plot, phase angle plot. So these things always you have to keep in your mind. So therefore we can say Bode analysis is going to use the two plots, one is for the magnitude and the other for the phase angle plot. So these things always you have to keep in your mind. So magnitude plot is nothing but magnitude plot means I already told you what is the magnitude plot and the phase angle plot also. These two formulas always you have to keep in your mind. So if you remember this one, you can draw anything in an easy manner. Now the next point is Nyquist plot uses the polar plot only. I already told you. So we are going to draw the Nyquist plot by using only the polar plot. So for the four junctions, for the four things we are going to draw the polar plot. From J-axis. J-axis means we can say, I already told you, I have drawn the graph. So basically, this is the, we can say, this is basically S plane, RHS of the S plane. So now, all these junctions we are going to draw for each and everything. So, for this one we are going to draw the polar plot, and for this one we are going to draw the polar plot, and for this one we are going to draw the polar plot, Again for this one also we are going to add the polar plot. Total 4 things. So for this one, 1, 2, 3, 4. So total for 4 things we are going to have the polar plot. So therefore we can say in simple words, Nyquist plot is going to use only the polar plot only. So Nyquist plot will use only the polar plot only. So Nyquist plot is going to use only the polar plot only. So with the help of polar plot we are going to have the Nyquist plot. The next point is the relative stability can be accessed from both the Nyquist analysis as well as the Bode analysis. So relative stability can be accessed from both the Nyquist as well as the Bode analysis. So relative stability can be accessed from both the Nyquist analysis as well as the Bode analysis. Even through the Rose-Hall criteria also we can figure out the relative stability. So relative stability can be accessed from the Rose-Hall criteria, Nyquist analysis as well as the Bode analysis. So this one always you have to keep in mind. So relative stability can be accessed from the Rose-Hall criteria, Bode analysis as well as the Nyquist analysis. So we can say the relative stability can be accessed from the RH criteria, Nyquist analysis as well as the Bode analysis. So finally I can say the relative stability can be accessed from RH criteria, Nyquist analysis as well as Bode analysis. The next point is a distinct pole always lies on the real axis. A distinct pole always lies on the real axis. I already told you a distinct means different poles. Whenever the different poles are going to lie on the real axis, it means that the damping ratio is greater than 1. I have already told this important point. A distinct poles always they are going to lie only on the real axis. It means that the damping ratio is greater than 1. So a distinct pole always they are going to lie on the real axis. It means that the damping ratio is greater than 1. A dominant pole has a large standing constant. I have already told you the dominant pole is a pole which is very closer to origin is called as a dominant pole because it has the large standing constant means it will take a lot of time in order to decay. Whereas insignificant pole is a pole which is far away from the origin is called insignificant pole. It has a very less time constant, so within a small amount of time it is going to decay. So finally I can say a dominant pole means a pole which is very closer to origin. It is a very large time constant means it will take a lot of time in order to decay it's a transient response. Whereas an insignificant pole means a pole which is very far away from the origin, which is a very less time constant means within less amount of time it is going to decay. The next point is the neutral zone is also known as the dead band. The neutral zone is also called as the dead band. The neutral zone is also known as the dead band. What's the meaning of dead band? Even though input is non-zero, but still you are going to get output is equal to 0. That is called as the dead band. Even though input is not equal to 0, but still the output is equal to 0. That is called as the neutral zone. A neutral zone is also known as the dead band. So the neutral zone is also known as the dead band. It indicates that even though input is not equal to 0, but still the output is equal to 0. That is called as the dead band. The next point is the controller action of a two-position controller is very similar to that of a pure on-off controller. The controller action of a two-position control is very similar to that of a pure on-off controller. Two position means we can say on or off. So two position, one position is two position means we have two positions. It is similar to that of a on-off controller. The controller action of a two-position controller is very similar to that of a pure on-off controller. So if you on one thing you are going to do and if you off you are going to do another thing. So basically it is like a two position. So therefore we can say the controller action of a two position controller is very similar to that of a pure on-off controller. So we can say the controller action of a two position controller is very similar to that of a pure on-off controller. So we can say the controller action of a two position controller is very similar to that of a pure on-off controller. So the controller action of a two position controller is very similar to that of a pure on-off controller. So therefore we can say the controller action of a two position controller is very similar to that of a pure on-off controller. So if you on, you will get one position. If you off, you will get another position. So this is similar to that of a two-position controller. So therefore, we can say the controller action of a two-position controller is very similar to that of a pure on-off controller. The next point is air conditioning system works essentially on a two-position control basis. Air conditioning system works essentially on a two-position control basis. So basically, I can say that air conditioning system basically works essentially on a two-position control basis. So basically, suppose if you on the air condition, you will get cool. If you off it, it will become 0. So basically, we can say that the air conditioning system works essentially on a two-position control basis. Suppose if the temperature is exceeding the means we can say if the temperature is exceeding the prescribed temperature, then we should automatically it should get turned off. Suppose if the temperature is lesser than the prescribed temperature, then it should get on in order to make it a desired temperature. So we have two positions, on and off. So it is similar to that of a two-position control. So therefore, air conditioning system works essentially on a two-position control basis, because whenever the temperature is lesser than the prescribed temperature, then automatically it should on in order to get the prescribed temperature. If the temperature is greater than the prescribed temperature, then it should get off in order to decrease the temperature to the prescribed temperature. So we have two positions, on position and the off position. So therefore, we can say air conditioning system works essentially on a two-position control basis. The next point is the pole nearer to j omega axis has a larger time constant due to less negative real part. I've already told you the pole nearer to j omega axis has a larger time constant due to the less negative real part. So this pole has a dominant pole and it takes a lot of time in order to get decay. But a pole which is very far away to the j omega axis has a lesser time constant because it has the very large negative real part, and within a less amount of time it is going to get decay. So listen carefully. A pole near to j omega axis is pole as a dominant pole which has a large time constant because due to less negative real part it will take a lot of time in order to get decay. Whereas a pole which is very far away to the j omega axis is called as the insignificant pole because it has a very small time constant because it has the very large negative real part. But within a small amount of time it is going to get decay. The next point is servo motors should have the low inertia which can be obtained by small diameter and large length. I have already told you servo motor. A servo motor should have the low inertia which can be obtained by a small diameter and large length. Just now we have discussed servo motor. So the servo motor it will have small amount of diameter but large amount of length, and the X-bar ratio is very small. I have already told you here for servo motor the X-bar ratio is very small. Yes, the resistance is very low when compared to the reactors. So we can say servo motor should have the low inertia. It indicates that it should have less amount of diameter with a large length. So therefore, X-bar ratio is very small. The next point is when a transfer function model is converted into a state space model, the order of the system may be reduced because of the pole zero cancellation takes place. So when transfer function model is converted into a state space model, the order of the system may be reduced due to the pole zero cancellation that may occur. So basically when you are trying to convert a transfer function model into a state space model, the order of the system may be reduced because of the pole zero cancellation. So listen carefully. When a transfer function model is converted into a state space model, the order of the system may be reduced because of the pole zero cancellation. So remember, when a transfer function model is converted into a state space model, the order of the system may be reduced because of the pole zero cancellation. So listen carefully. When a transfer function model is converted into a state space model, the order of the system may be reduced because of the pole zero cancellation. Because of pole zero cancellations, the order of the system may be reduced. So therefore, finally I can say, when a transfer function model is converted into a state space model, the order of the system may be reduced because of the pole zero cancellation. I am going to discuss the other point. Listen carefully. To make the linear torque slip characteristics in a linear servo motor, the ratio of the SVR should be low. The motor has the high resistance. So basically, I already told you to make the linear torque slip characteristics in the case of linear servo motor, the ratio of the XYR should be very, very low. It indicates that the rotor resistance is high value when compared to the value of X. So this part I wanted to show the number of times. See, whenever we are going to compare the induction motor as well as servo motor, the XYR ratio of the induction motor is larger when compared to the XYR ratio of the servo motor. So therefore, we can say for servo motor, the XYR ratio is very, very less. It has low inertia, means less diameter but large length. So therefore, we can say to make the linear closed slip characteristics in the case of the linear servo motor, the ratio of the XYR should be low, which indicates that the rotor has the high resistance when compared to rotor reactance. The next point is, in order to use the Raoult-Hall criteria for determining the stability of the sample data system, the characteristic equation is 1 plus G of z H of z is equal to 0 should be modified by using bilinear transformation of z is equal to r plus 1 by r minus 1. This is basically for the discrete time system. For discrete time system, for the sample data system, the characteristic equation is 1 plus G of z H of z is equal to 0, and the bilinear transformation formula is z is equal to r plus 1 by r minus 1. So always remember, in order to use the Raoult-Hall criteria for determining the stability of the sample data system or discrete time system, the characteristic equation is 1 plus G of z H of z is equal to 0 should be modified by using bilinear transformation of z is equal to r plus 1 by r minus 1. So we can say, in order to use the Raoult-Hall criteria for determining the stability of the sample data system, the characteristic equation 1 plus G of z H of z is equal to 0 should be modified by using the bilinear transformation of z is equal to r plus 1 by r minus 1. So finally I can say, in order to use the Raoult-Hall criteria for determining the stability of the sample data system, the characteristic equation 1 plus G of z H of z is equal to 0 should be modified by using bilinear transformation of z is equal to r plus 1 by r minus 1. So finally I can say, in order to use the Raoult-Hall criteria for the determining the stability of the sample data system of discrete time system, the characteristic equation is 1 plus G of z H of z is equal to 0 should be basically modified by using the bilinear transformation, which is z is equal to r plus 1 by r minus 1. The next point is, the Laplace transform of a transportation lag of 5 seconds is T of s is equal to e to the power of minus 5. So basically, suppose you can see there is output y of t is equal to x of t minus a. This output is the delay of the input by a seconds. And what is the transfer function? After the Laplace transform both sides, we are going to get y of s is equal to e to the power of minus as into x of s. So y of s by x of s is equal to transfer function, which is equal to e to the power of minus 5 minus as. And a is nothing but 5 seconds. So in substitute, we are going to get e to the power of minus 5 s. So therefore, we can say simply, the Laplace transform of a transportation lag of 5 seconds is T of s is equal to e to the power of minus 5 seconds. Even if you don't remember the formula, so you can easily derive it from this equation, which is output is the delay of the input by a seconds. So y of t is equal to x of t minus a. So if you apply the Laplace transform on both sides, we are going to get y of s is equal to e to the power of minus a into x of s. The transformation is y of s by x of s is equal to e to the power of minus a. Where a is equal to 5, the substitute we are going to get the result. The next point is, if any time delay present in the system, then it shows in the form of zeros in the RHS of the S plane and G of s, H of s. If any time delay present in the system, then it shows in the form of zeros in the RHS of the S plane and G of s, H of s. So what is the meaning of this one? Suppose if there is any time delay, present in the system, then it is going to show in the form of zeros in the RHS of the S plane. So this one always you have to keep in your mind. So therefore we can say, suppose if there is any delay present in the system, then it can be easily shown with the help of zeros which are going to present in the RHS of the S plane in G of s, H of s, open loop transfer function. If any time delay present in the system, then it shows in the form of zeros in the RHS of the S plane by G of s, H of s. Suppose if you got the G of s, H of s open loop transfer function, and if you plot the pole zero plot, and if you see zeros which are present in RS of X plane, it indicates that here some time delay elements are present. So listen carefully, some time delay is present in the system. So finally, in simple words I can say, suppose if there is an open loop transfer function g of h of s, if you draw the Poincare plot of this open loop transfer function, and if you see some zeros are present in RS of H plane, it indicates that there is some type of time delay which is present in this open loop transfer function. So finally, in simple words I can say, suppose if you take a open loop transfer function g of h of s, and if you draw the Poincare plot of this open loop transfer function, and if you see any zeros which are present in the RHS of H plane, it indicates that some type of time delay is present in this system. So we can say finally, if any time delay present in a system, then it shows in the form of zeros in the RHS of the H plane in open loop transfer function g of h of s. The next point is, in proportional controller, the amount of the selection error is always directly proportional to 1 by Kp, whereas P of s is equal to Kp into T of s. So this one always you have to keep in your mind. So in the case of proportional controller, what is the output P of s, what is the input E of s? So P of s is equal to Kp into E of s, and the steady state error magnitude value is directly proportional to 1 by Kp. So as the Kp increases, the amount of this steady state error will decrease. So this one always you have to keep in your mind. So in the case of proportional controller, the output is P of s and the input is E of s. So P of s is equal to Kp into E of s, where Kp is the proportional controller gain, and the amount of the steady state error is directly proportional to 1 by Kp. So as the value of Kp increases, the amount of this steady state error will decrease. The proportional controller is a natural extension of an on-off controller. So the proportional controller is basically a natural extension of an on-off controller. The proportional controller is basically a natural extension of the on-off controller. So we can say the proportional controller is basically a natural extension of an on-off controller. So basically, the proportional controller is basically a natural extension of an on-off controller. The next point is, the disadvantage of proportional controller is it exhibits a residual error known as the offset. The disadvantage of the proportional controller is it is going to exhibit a residual error known as the offset. Means there is still some non-zero steady state error is going to be present all the time. So this is one of the main disadvantage. The disadvantage of the proportional controller is it is going to exhibit a residual error which is known as the offset. The disadvantage of the proportional controller is it is going to exhibit some residual error which is known as the offset. Means there is still some non-zero steady state error is going to still present in this proportional controller. In this control action is provided 100% or not, that is 0%. Means either control action can be either 100% or 0%, but not between these two things. Only two things can be provided, either 100% control action or no control action. So this one always you have to keep in your mind. So finally, I can say some important points regarding this proportional controller is, in the case of proportional controller, the output is P of s and the input is E of s, and Kp is the gain of the proportional controller. So P of s is equal to Kp into E of s, and the amount of this steady state error is directly proportional to 1 by Kp. As the value of Kp increases, the amount of this steady state error will decrease. The proportional controller is basically a natural extension of an on-off controller, and the main disadvantage of the proportional controller is it is going to exhibit a residual error which is known as offset. Still a non-zero steady state error is going to present all the time. In this, control action is provided either 100% or not, that is 0%. So these things always you have to keep in your mind. Now the next point is, the disadvantage of the imperial controller is its response to error is slow. However, it is capable of eliminating the steady state error completely in a system or the plant, and the stability is going to get decreases. I have already told the disadvantage of the imperial controller is the response to error is very slow. Means the rise time is very low. However, it is capable of eliminating the steady state error completely in the system or plant. Means the steady state error is equal to 0, and the stability is going to get decreases because for number of poles, the number of poles are increases, the pole loss is going to shift to the rest of H plane, so stability will decrease. So therefore we can say, with the help of imperial controller, the response, the rise time is going to get increases for the steady state error will decreases and finally it will become 0. Whereas the stability is going to get decreases because more number of poles means the root cause is going to shift the axis of S plane. So therefore the stability will decrease. So finally I can say the disadvantage of the internet controller is its response to error is very slow, means the rise time is very more. However, it is capable of eliminating the steady state error completely in the system or plan, means the steady state error is equal to 0 and the stability is going to get decreases because more number of poles. So therefore the root cause is going to shift to the rest of the S plane. So therefore the stability will decrease. The next point is in derivative controller, it does not eliminate steady state error properly. It only improves the transient state characteristics of the system. So I have already told you, integral controller. See, the derivative controller, it does not eliminate the steady state error properly. It only improves the transient state characteristics of the system. I have already told this point. The lead compensator means derivative controller. So lead compensator is basically used to improve the transient response. So therefore the rise time is going to get decreases. The speed of the response will increases. But it will never eliminate the steady state error. It does not eliminate completely the steady state error, means there will be still some amount of final steady state error. So in derivative controller, it does not eliminate the steady state error properly. It only improves the transient state characteristics of the system, means the rise time is going to get decreases. So what I told you, derivative controller is nothing but lead compensator. So therefore we can say in derivative controller, it does not eliminate the steady state error completely or properly. It only improves the transient state characteristics of the system, means the rise time is going to get decreases. So therefore the speed of the response will increase. This is also known as the anticipatory controller because it sends control signal in anticipation of error. This anticipatory nature will result in large instability. The derivative controller cannot respond to sudden errors. So listen carefully. This is also known as the anticipatory controller because it sends control signals in anticipation of the error. This anticipatory nature will result in large instability. So therefore the derivative controller cannot respond to sudden errors. So therefore you can say these are some of the important points regarding the derivative controller. So this derivative controller is also called as the anticipatory controller because it is going to send the control signal in anticipation of the error. This anticipatory nature will result in large instability. So therefore the derivative controller cannot respond to sudden errors. So we can say finally this derivative controller is also known as the anticipatory controller because it is going to send the control signal in anticipation of the error, and this anticipatory nature will result in a large instability. So therefore the derivative controller cannot respond to the sudden errors. So finally I can say this derivative controller is also called as the anticipatory controller because it is going to send the control signal in anticipation of the error. This anticipatory nature will result in a large instability. So therefore the derivative controller cannot respond to sudden errors. The next point is by using a rate controller of tachometer feedback on secondary system, the steady state error will increases, the time constant will decreases, and the damping ratio will increases, and omega n is equal to constant. What is the time constant T? T is equal to 1 by zeta omega n. So omega n is equal to constant. As zeta is increases, so therefore the time constant is going to get decreases. So you can see by using the rate controller or the tachometer feedback on a secondary system, the steady state error is going to get increases and the damping ratio is going to get increases, whereas the natural frequency is equal to constant. So even the time constant T is equal to 1 by zeta omega n. As zeta increases, omega n is constant, so therefore the time constant will decrease. So finally I can say by using the rate controller or tachometer feedback on the second order system, the steady state error will increases and the damping ratio increases, whereas the natural frequency is equal to constant. Time constant for the second order system is equal to 1 by zeta omega n. As zeta increases, omega n is constant. The time constant is going to get decreases. So these things always you have to keep in your mind. The next point is in PD controller is similar to phase shift compensator, which is basically used to improve the transient state but have some steady state error. So PD controller is similar to phase field compensator, which is basically used to improve the triangle state, but will have some steady state error. I've already told you PD controller is nothing but it is a phase field compensator. It is basically used to improve the transient state characteristics only, but have some steady state errors. I've already told you. See, this is a PD controller. It is nothing but, see, whenever you are going to use the PD controller is very similar to PD compensator. It is basically used to improve the transient state characteristics, but if you have some sensitive errors, the rise time is going to get decreases. So rise time to bandwidth is always equal to constant. So as rise time decreases, the bandwidth will increases. And also I've already told you that the damping ratio is always going to get increases. So peak quantity is going to get decreases. So this one I've already told you. And one more important point is steady state error. See, it is basically it is going to decrease. See, it is going to improve the transient responsiveness. It will be with the steady state. So therefore, the steady error will decrease. So this point always you have to keep in mind. The next one is that the PD controller is capable of improving the transient state characteristics, that is, speed of the response of the system only. Same thing I already told you. So PD controller is capable of improving the transient state characteristics, that is, speed of the response of the system only, means it is going to degrade the steady state characteristics of the system. It will only improve the transient state characteristics of the system, but it will degrade the steady state characteristics of the system. So for sensory input, the phase of the controller output leads by tan inverse of omega into PD. Hence it is similar to phase shift compensator in terms of the filtering property. And it is analogous to, you can say, high pass filter. It is a lead compensator. I have already told you basically these are some of the points within the PD controller. In the case of PD controller, it is similar to phase shift compensator. The output is going to lead the input by some amount of angle. The angle is again tan inverse of omega PD. So therefore, we can say it is similar to a high pass filter. It is similar to a high pass filter. I have already told you lead compensator is basically it's a high pass filter, because in the case of these compensators, zero is going to come earlier than pole. So 0 means we can say plus 2 decibels per decade. After that, we are going to get a pole of minus 20. So plus 20 minus 20 is 0 dB. So we are going to get a high pass filter. So therefore, we can say for final input, the phase of the controller output leads by tan inverse of omega 3D. Hence, it is similar to phase the compensator in terms of filtering property, and it is analogous to the high pass filter. So therefore, we can say that basically, I've already told you the phase field compensator. See, this PD controller is similar to phase field compensator. So output is going to lead the input by some amount of angle. It is equal to tan inverse of omega PD, and it is analogous to high pass filter. So then what is going to happen? As I've already told you, what are the effects with the help of PD controller? As I've already told you, it is going to improve only the transient state characteristics of the system. So therefore, the rise time is going to get decreases. As the rise time decreases, the bandwidth is going to get increases. As you can see clearly, because the rise time to bandwidth is always equal to constant. And I've already told you in all three cases, the damping ratio is going to get increases. So B equals to decrease, because the damping ratio with B equals to inversely proportional. Then, whenever you are going to use a PD, means differentiator. Whenever you are going to use a differentiator, the noise is going to get improved. I already told you, whenever you are going to use a differentiator, the noise is going to get improved. It's going to get increased. So simply the noise will decrease. So whenever PD means basically we are adding zeros. So if you are adding zeros means the stability will increase or improves, because whenever we are adding zeros, the stability will improve and the steady state error will decrease, or we can say it will increase. I already told you the steady state error will actually it will increase. It is going to degrade the steady state error, whereas the natural frequency is always equal to constant in this case. So it is going to improve the steady state accuracy, but completely it will not eliminate the steady state error. So there will be some amount of steady state error always. So it is going to improve the steady state accuracy, but completely it will not eliminate steady state error. So it is going to improve some amount of steady state accuracy, but still it can't eliminate the completely steady state error. Means there will be still some amount of steady state error is always going to get present. So with the help of this one, we can say the type of system is not increased, power of the system is also not increased. So with the help of this compensator, the type of the system is not increased, as well as the RO system is also not increased. So these things always you have to keep in your mind. Now the next point is In the case of PI controller, I have already told you, PI controller is nothing but it's a lag compositor. It is used to improve. It is basically used to improve only the transient response. So it is basically used to improve only the steady state response. So therefore, it will degrade the transient response. I have already told you, it is going to improve the steady state response means it will degrade the transient response. Therefore, we can say the steady state error will become 0. The steady state error will become 0. It is going to degrade the transient response with the rise time will increase. So bandwidth will decrease because therefore it is always equal to constant. As the integral is 1 by s terms, as the poles are going to get increases, so therefore the root is going to shift the s of s plane. So therefore the system instability is going to get decreases. So therefore the stability of the system is going to get decreases. And I already told you in all the three cases, the damping ratio is going to get increases. So therefore the peak quotient will decrease. The damping ratio is going to get increased. So therefore the peak quotient will decrease because both are inversely proportional. It is going to increase the type as well as the order of the system by 1 because 1 by s means it is going to increase the type as well as the order of the system by 1 because it is going to add one pole at the origin. So integral is 1 by s. So because of this, it is going to increase. So it is going to increase the type of the system as well as the order of the system by 1 because it is going to add pole at the origin. It is in terms of filtering property, it is analogous to low pass filter. I have already told you here in the case of a lag compensator, we can say the output is going to lag the input. So therefore, the pole is near the origin when compared to 0. So pole means we can say minus 2 response for decade, then 0 you are going to get. So therefore, you are going to get minus 20 plus 20 is about 0 dB. So you are going to get a low pass filter. We are going to get a low pass filter. So these things always you have to keep in your mind. So therefore, we can say in the case of PI controller, as I have already told you, if it is going to improve the steady state response means it will decrease the transient response. So steady state error is equal to 0. So it is going to decrease the transient response means the rise time will increase. So bandwidth will decrease because the dot is always equal to constant. As the number of poles are increases, the stability of the system will decrease. Now in three cases, the damping ratio is going to get increases. So therefore the peak quotient will decrease. I have already told you. Then it is going to increase the type as well as order of the system by 1 because it is going to add pole at the origin. And it is similar to a low pass filter. The next point is in the PID controller, it is going to improve both the transient characteristics as well as the steady state characteristics. So therefore, in the case of PID controller, it is going to improve both the transient characteristics as well as the steady state characteristics. So therefore, we can say in the case of PID controller, it is going to improve both the transient state characteristics as well as the steady state characteristics. So basically, PID is nothing but it is similar to lag loop compensator. I have already told you. In terms of filtering, it is analogous to band reject filter. So this is also I have already told you. So now it is going to improve both the transient response as well as the steady state response means the rise time is going to get decreases because it is going to improve the transient state characteristics. As the rise time decreases, bandwidth will increase because both of them are inversely proportional. Because the dot is always equal to constant. Then you can see basically whenever you use a differentiator, whenever you use a differentiator, noise is going to get increases. So signal noise ratio is going to get decreases here because noise is going to get here increase. So because of that, signal noise ratio is going to get decreases. Stability is going to get improves. Why it is like this? Because stability is going to get improves because here you can see basically there is a D terms are there. Differentiator means S terms are J terms are added. So because of this, stability is going to get increases. And I have already told you in all three cases, the damping ratio is going to get increases. So therefore, the peak quotient will decreases because both are inversely proportional. I have already told you it's also going to improve the steady state response. So steady state is equal to 0. It is going to increase the type as well as the order of the system by 1 because if there is an integrator, so 1 by its terms. So it is going to increase the type as well as the order of the system by 1. Always it is going to give high priority. Always give high priority for PID controller in order to have the least error in output among any other controller. Always give high priority for the PID controller in order to have the least error in output among any other controller. Suppose if you want to choose PD, PI, PID out of this, which controller if you want to choose, if you have the minimum size of the revenues, always try to go for the high priority, which is a PID. So always give high priority for the PID controller in order to have the least error in output among any other controller. So suppose if a designer and if you want to design an output, if you want to have the least suggested error, then always try to prefer the PID controller only, because in this controller you will always try to get a output of any least error. So therefore we can say that always give high priority for the PID controller in order to have a least error in the output among any other controllers. So this one always you have to keep in your mind. So always give high priority for the PID controller in order to have the least error in output among any other controller. So this point always you have to keep in your mind. So now the next point is root sensitivity function. Root sensitivity function is I've already told you. The root sensitivity function is sensitivity of s with respect to k, which is called as the root sensitivity function. Sensitivity of s with respect to k means I've already told you here s means here s, here k means here k. So k by s equal to ds by dk. S is called as a closed loop poles and k is called as a system gain. So S is called as a closed loop k poles as well as k is called as a system gain. Therefore we can say the root sensitivity function of the sensitivity of s with respect to k is equal to k by s into ds by dk. S is called as a closed loop poles whereas k is called as a system gain. So therefore we can say the root sensitivity function means sensitivity of s with respect to k, that is that k by s into ds by dk, where s is called as a closed loop poles and k is called as a system gain. The next point is the critical dam systems are highly sensitive to noise. I already told you that critical dam systems are highly sensitive to noise. So critical dam systems are highly sensitive to noise, and I already told you in the industrial computers we always try to design any system with that critical dam response because there will be no oscillations. But still the systems are very sensitive to noise. The critical dam systems are highly sensitive to noise. The next point is number of separate root locks is always equal to poles or zeros whichever is larger. We already told you number of root locus branches is always equal to the maximum value of either P or Z. P is the number of open loop poles and Z is the number of open loop zeros. Out of this, whichever is the maximum, that value is the number of root locus branches. So number of separate root locus is equal to the number of poles or zeros whichever is larger. I already told you, so the number of root locus branches is always equal to the maximum value of P comma Z. P means number of open loop poles and Z means number of open loop zeros. Out of this, whichever is the maximum, that is nothing but number of root locus branches. The next point is an addition of real zero at s is equal to minus z naught in the transfer function g of h of s of the control system results in the increase of the stability margin, because an addition of a real zero at s is equal to minus z naught in the transfer function g of h of s will take the resulting root locking bend towards the left of the s plane. So we already told basically what is the meaning of this one. So whenever you are going to add any zero to the whenever you are going to add any zero in the ellipse of the s plane to the open transfer function, then the root is going to shift in ellipse of s plane, so the shadow of the system will increase. Since a isolated zero is not physically realizable, we must add a pole along with the compensating zero so as to achieve physical reliability. The compensator having such transfer function is known as the lead compensator, as the pole must of course be added far away from the geometric axis such that it has a relatively negligible effect on the root locus in the region. As you know, a lead compensator speeds up the transient response and increases the margin of stability of a system. So what I am trying to tell you is very simple. See, basically, suppose if you want to increase, suppose what is going to happen? Suppose if you add a zero in the rest of s plane, then the open transfer function g of h of s, then definitely we can say the root locus is going to shift to the LS of s plane. So therefore, we can say that the stability of the root, the stability of the closure system is going to be increases because the root is going to bend to the LS of s plane. So how to add a isolated zero? So practically you cannot add a isolated zero. Always you have to add a zero with a pole. So two things are going to come in pair. You can't add individually. You can't add individually a pole or you can't add individually a zero. Always you have to make it come in a pair. So if you want to add a zero, then pole should be added very, very far away from the origin. So therefore pole will have less amount of effect in the root locus or the root locus. So definitely 0 should be very near dominant 0, but insignificant 4. This is possible only in the case of lead compensator. So we try to use the lead compensator because it has a dominant 0 and a insignificant 4. So now with the help of this one, we try to add a in order to bring this the root law constituents of this plane. So therefore the system will be very stable. So finally I can say, and I already told with the help of lead compensator is going to speed up the transient response, and also it is going to increase the margin of stability of a system. Stability is going to get increases because of the lead compensator, because whenever you are going to add zeros, definitely we can say the stability is going to get increases. So this one I already told you so many number of times. So therefore we can say finally an addition of the real 0 at s is equal to minus z0 means in the s of s plane in the transfer function of the upper transfer function 0 h of s of a control system, which is going to result in the increase of the stability margin, because an addition of real 0 at s is equal to minus z0 in the transfer function 0 h of s will take the resultant root locate them towards the ellipse of the s plane. Since the absolute 0 is not physically realizable, we must add a pole along with the compensator 0 so as to achieve physical realizability. The compensator having such transfer function is known as the lead compensator, as a pole must of course be added far away from the geometric axis such that it has the relatively negligible effect on the read locus in the region. As we know, a lead compensator speeds up the transient response and increases the margin of stability of a system. So finally, the simple words I can say, suppose if we add a 0, a real 0, and then into relaxes the rest of s plane, then to the overall transfer function, then the root locus is going to shift to the left of to the s of s plane, so therefore the system stability will increase. But adding a 0 isolated 0 is impossible. So always adding a isolated pole is also impossible. We have to add always 0 and pole in a pair. So therefore, if you want a dominant 0 but insignificant pole, it is possible only in the case of lead compensator. For lead compensator, there will be a dominant 0 and an insignificant pole. So if you add this one with a given open transfer function, definitely the root of it is going to shift to the rest of s plane. The stability will increase. And I already told you, the lead compensator is basically it is going to speed up the transient response, and also it is going to increase the margin of stability of the system. Yes, we can say the stability of the system is going to get improved because of the lead compensator. Because lead compensator means PD controller means derivative means we can say that 0 terms like that shortcut to remember, so therefore the stability will increase. The next point is the addition of a pole to the forward part of the transfer function. The closed loop transfer function becomes less stable because the resistance increases and the bandwidth decreases. So I've already told you, the addition of a pole to the forward part of the transfer function, the closed loop system becomes less stable, the resistance increases and the bandwidth decreases. Why it is like this? Because I've already told you, whenever we are going to add a pole to the open loop transfer function or the forward part of the transfer function, then the root locus is going to shift to the RHS of S plane. RHS of S plane. So therefore the system stability will decrease. The system stability will decrease. And also, you see, pole terms will simply we can say 1 by S integrator. Shortcut remember 1 by S integrator. So 1 by S means we can say it is a lag compensator. So lag compensator. So lag compensator is basically it is going to improve only the steady state response and it is going to degrade the transient response. So therefore the resistance is going to get increases and the bandwidth is going to get decreases. So this one I already told you so many number of times. So therefore we can say that whenever you are going to add a pole to the open loop transfer function, we can say that whenever you are going to add a pole to the open loop transfer function, the root loop is going to shift to the RS of S plane. So therefore we can say the system stability will decrease. Pole is ultimate, simply we can say PI controller or lag compensator. So therefore the lag compensator is basically used to improve only the stretched characteristics, means it is going to decrease the transient response. So therefore resistance is going to get increases and the bandwidth is going to get decreases while the stretched will be 0. So these things always you have to keep in your mind here. The next point is adding a pole to the open loop transfer function G of H of S has the effect of pushing the root locus toward the RHS in the S plane, because if the number of poles increases, the angle of asymptotes for the complex roots is reduced. So basically, you can see clearly, adding a pole Adding a pole to the open transfer function g of h of s has the effect of pushing a root locus toward the RHS in the exponent, because if the number of poles increases, the angle of asymptotes for the complex roots is reduced. So you can see basically that the angle between the asymptotes. What is the angle between the asymptotes? Angle between the asymptotes is nothing but which is equal to 2 pi by p minus z. As the number of poles increases, 2 pi by p minus z. So p minus z is going to get increases. So therefore, as the denominator increases, so overall angle is going to get reduces. So I have already told you, as the overall angle reduces, so therefore the root locus is going to shift to the RHS of the exponent. So therefore we can say, whenever you are going to add a pole to the open transfer function g of h of s, then the root locus is going to shift to the RHS of the exponent, because whenever the open poles are increases, the angle between the asymptotes is going to get reduces. So therefore the root locus is going to shift to the RHS of the exponent. What is the angle between the asymptotes? 2 pi by t minus z. As the t increases, the denominator increases, so overall value is going to get reduces. So finally I can say, adding a pole to the open transfer function g of h of s, it has the effect of pushing the root locus toward the RHS of the exponent, because if the number of poles increases, the angle between the asymptotes for the complex roots is going to get reduced. The next point is, root locus can be used for analyzing stability as well as the transient performance. Root locus can be used for analyzing the stability as well as the transient performance. Yes. See, by seeing the root locus, we can say, if the root locus is going to lie in the RHS of exponent, we can say the system is said to be stable. But if the root locus is going to lie on the RHS of exponent, then we can say the system is said to be unstable. So by seeing the root locus, we can say whether the system is stable or unstable. And also the transient performance also. Suppose if the root locus are purely real and equal, means we say it's a critical down system. If the root locus is having a real poles but which are not equal, then we can say it is a overdamped system. But if the root locus are complex conjugate with the real part and the complex poles, we can say then it is said to be undamped system. If the root locus are purely imaginary, then we can say undamped system. So based on this also we can say about the transient response. How the transient response is going to have, either oscillations are going to present all the time, or whether the oscillation is going to reduce as time goes on, or there is no oscillations with a purely exponential, or you can say that there is no oscillation but purely exponential with a sluggish in nature. So all these transient response also we can analyze just by seeing the nature of the roots on the root locus. So therefore we can say, by seeing the root locus we can tell given system is stable or unstable, and also we can comment on the transient performance also. The root locus can provide insight into the system stability and also performance also. I have already told you. So root locus, they are going to provide the insight into the system stability and also performance. Means for what range of k the system is stable, for what range of k the system is unstable, and what is the performance for different values of k, what is the performance of the system also we can easily get to know all this information. Then shape of the root locus gives an idea of the type of controller needed to meet the design specification. So just by seeing the shape of the root locus, then we can design, we can have an idea of what type of controller we need to use in order to meet this design. Just by seeing the shape of the root locus, we can get an idea of what type of controller we need to require in order to meet this design specification also. So just by seeing the shape of the root locus, we can have an idea of what type of controller we need to use in order to meet this design specifications. The next point is that root locus can be used to handle only one variable at a time. If you want to handle more variables at a time, then go for the state space analysis. I've already told you. So root locus is basically it can be used to handle only one variable at a time. But if you want to handle more number of variables at a time, then go for the state space analysis. So basically you can say that in the case of root locus, only one variable is varied at a time. But in the case of state space analysis, you can vary any number of variables. So root locus can be used to handle only one variable at a time. But if you want to handle more variables at a time, then go for the state space analysis. The next point is that the intersection of the asymptotes must always be on the real axis. I already told you The intersection of the asymptotes must always be on the real axis. It may be part of the root locus or it may not be part of the root locus also. And I've already told you that the intersection point of the asymptote is Polaris centroid, and its formula also I've already told. Sigma comma 0 is equal to summation of all the poles minus summation of all zeros by total number of poles minus total number of zeros comma 0. With this point also I've already told you. The next point is the asymptotes of the root loci are referred to the angle of root loci when the system J is infinity. The asymptote of the root locus refer to the angle of root loci when the gain k is infinity. So basically, when the gain of the k is infinity, then the root locus is going to match with that of the asymptotes. When the value of the k is going to infinity, then the actual root locus is going to match with that of the asymptotes. The asymptote of the root loci refer to the angle of root loci when the gain k is infinity. When the value of the gain k is infinity, then the root locus is going to match with that of the asymptotes. Hence, they are going to move in the same direction as the asymptote. The next point is the value of the system gain at any point on a root locus can be obtained as a ratio of the product of lengths of the vectors from the poles to that point to the product of lengths of the vectors from zeros to that point. I already told you. Suppose if you want to confirm whether a given point is present on a root locus or not, this can be get only with the help of the angle criteria. So with the help of angle criteria, we can say any given point and they explain whether it is a part of root locus or not. Suppose it is a part of root locus, then for what value of k we are going to get that root, we can get with the help of Navier criteria. So with the help of Navier criteria, you can get the value of k. See, and this point I have already told you so many number of times. The next point is the relative stability of the system increases with the effect of adding the zero to the system. The relative stability of the system increases with the effect of adding zero to the system. I already told you, if you are going to decrease the gain of the system, then also we are going to increase the stability of the system, or if we add the zero also, then also we are going to increase the stability of the system. So in these two methods, we can increase the stability of the system. Therefore, we can say the stability of the system can be improved by two methods, either by decreasing the gain of the system or either by adding the zeros to the system. So therefore, we can say that we can increase the gain, we can increase the stability of the system either by decreasing the gain of the system or adding the zeros to the system. Because if you are going to add the zeros to the system, the root locus is going to shift to the rest of the plane. So therefore, we can say the system is said to be more stable in nature. So the relative stability of the system increases with the effect of adding zeros to the system. So if we add zeros to the system, double transfer function, the root locus is going to shift to the rest of the plane. So therefore, we can say the system is said to be more stable. So finally, I can say the relative stability of the system increases with the effect of adding zero to the system. So therefore, whenever you are going to add the zeros for the double transfer function, the root locus is going to shift to the rest of the plane. So therefore, the relative stability is going to get increased more and more. The next point is the network function n of s is denoted with a scale factor multiplied with the ratio of the zero factors with 4 factors, because when there are n zeros and m poles, then the poles at infinity are of multiplicity of degree of n minus 1 m. Similarly, when n less than m, then the zeros at infinity are of multiplicity of degree of n minus n. So basically, listen carefully. A network function n of s is denoted with the scale factor multiplied with the ratio of the zero factors with the pole factors. So basically, you can say n of s nothing, it is multiplied with the some factor into number of zeros by number of poles. Because when there are n zeros and m poles, suppose let me assume there are n zeros and m poles, then the poles at infinity are of multiplicity of degree of n minus n. So basically, what I am trying to tell you, suppose if the number of zeros are more than number of poles, then if number of zeros are more than number of poles, then the number of poles which are present at the infinity are of n minus n. Similarly, when n is less than m, means when number of zeros are lesser than number of poles, then the number of zeros at infinity are of multiplicity of degree of n minus n. So what I am trying to tell you is very simple. Suppose let me take some network function n of s. This is some multiplied factor k into, let me assume there are n number of zeros and m number of poles. Suppose if n is greater than m. If n is greater than m means we can say that number of zeros are more than number of poles. The number of poles which are present at infinity, which is nothing but n minus m. Similarly, suppose if n is less than m, means number of zeros are lesser than number of poles. Then number of zeros which are present at the infinity, which is equal to m minus n, because they already told you number of poles will be always equal to number of zeros. Some may be at finite, some may be at infinite. So overall, everything, both are always equal. So listen carefully. Number of zeros is always equal to number of poles. Some may be at finite locations, some may be at the infinite location, but overall, number of poles will be always equal to number of zeros. So we can say the network function n of s is denoted with a scale factor multiplied with the ratio of zero factors with the pole factors, because when there are n zeros and m poles, then if n is greater than m, then we can say the number of poles are infinity are of multiplicity of degree of m minus m. Similarly, when n is less than m, then the number of zeros at infinity are of multiplicity of degree of m minus n. So simply we can say, suppose that the network function n of s is having n zeros and m poles. Suppose if n zeros are, if the number of zeros are bigger than number of poles, then the number of poles which are at infinity is n minus m. Similarly, if the number of zeros are lesser than number of poles, then number of zeros at infinity are m minus n, because always the number of poles always equal to number of poles. Number of poles always equal to number of zeros. Some may be at finite locations, some may be at infinity locations. The next point is, you can say, the root locus is symmetrical about the real axis. It's a basic one. Root locus is basically symmetrical about the real axis. If a root locus branch moves along the real axis from an open loop from open loop pole to 0 or to infinity, this root locus branch is called as the real root locus branch. Listen carefully. If a root locus branch moves along the real axis from an open loop pole to open loop 0 or to infinity, this root locus branch is called as a real root locus branch, because this root locus branch is lying only on the real axis for all the time. So it is called as a real root locus branch. And I already told you the root locus branch is always going to start from open loop poles and it is going to end at the open loop zeros. The breakaway points of the root locus are the solutions of the dk by ds is equal to 0. I already told you the breakaway points of the root locus are the solutions of dk by ds is equal to 0, means first try to get the characteristic equation 1 with j by h is equal to 0 and try to get a k in terms of the equation of s. Now do the ratio of the derivative of k with respect to s plus dk by ds is equal to 0, and we are going to get some equation, and if we solve the equation we are going to get the value of s. So these are the roots at which the breakaway points are going to get occur. So now we need to check that these are the valid breakaway points or not. If you substitute the value of s in the characteristic equation and if you get the value of k positive, then these are the valid breakaway points. But if you get the value of k is negative, then these are the invalid breakaway points. The next point is inverse root locus is the image of the direct root locus. So we can say inverse root locus is basically the image of the direct root locus. And I've already told you, see, direct root locus I've already told you, inverse root locus also I've already told you, in detailed explanation also I've already told you. So therefore we can say inverse root locus is basically the image of the direct root locus. Open loop poles and zeros are used for the root locus plotting, and I've already told you the root locus is going to the root locus graph is going to start from the open loop poles and is going to end at the open loop zeros. So this one I've already told you. So with the help of open loop poles and open loop zeros only, we are going to plot the root locus. The next point is adding a zero lead to decrease in the angle of asymptote, so pushes the root locus to the left. And I've already told you, whenever you are going to add a zero to the open loop transfer function, the root locus is going to shift to the LH of the S-plane, so therefore stability is going to get increases. So adding a zero lead to the decrease in the angle of asymptote, so therefore it is going to push us the root locus to the left. So what I am trying to tell you, that basically we can say that, so by adding a zero to the open loop transfer function, we can say the root locus is going to shift to the LH of S-plane. But by adding a pole lead to the increase in the angle of the asymptote, so pushes the root locus to the right half of the S-plane. So we can say simply we can say that adding a pole to the adding a pole, adding a pole to the overall transfer function, it increases the angle of the ascent poles. So therefore, the root locus is going to shift to the RHS of S plane. So this one always you have to keep in mind here. So therefore, we can say that what is the angle formula? You know, the angle is 2q plus 1 into 180 by P minus Z. Suppose P is increased. If P is increased means we can say this denominator is going to get increases, so overall angle is going to get increases. So we can see basically that, so if P is increased means this overall angle, if P is increased means we can say that if P is increased means we can say this overall angle is going to get decreases. So therefore, the root locus is going to shift to the RHS of S plane. Suppose if Z is increased means this is going to get decreases, so overall is going to get increases. So therefore, the root locus is going to shift to the RHS of S plane. So this one always you have to keep in your mind. So listen carefully. When Z is increased means number of open loop zeros if it is increased, then what is going to happen? This denominator is going to get decreases, so overall value is going to get increases. So therefore, the root locus is going to shift to the RHS of S plane. Suppose if the number of poles are increases means this denominator is going to get increases, so overall angle is going to get decreases. So therefore, the root locus is going to shift to the RHS of S plane. So this point always you have to keep in your mind. So finally, I can say only one important thing, which is basically if you are going to add a 0 to the open loop transfer function, the root locus is going to shift to the RHS of S plane, because as the number of zeros are increases, the denominator is going to get decreases. So overall value is going to get increases. So therefore, the root locus is going to shift to the RHS of S plane. But this angle takes with respect to positive x-axis. Suppose if you are going to add the pole to the open loop transfer function, the root locus is going to shift to the RHS of S plane. The system will become unstable. Means if the number of poles are increases, the denominator is going to get increases. So overall angle is going to get decreases. So therefore, the root locus is going to shift to the RHS of S plane. So this point always you have to keep in your mind. The next point is complementary root locus refer to the root locus with the negative k. And already told you complementary root locus refer to the root locus with the negative k. I already told you regarding the complementary root locus. Complementary root locus means is a root locus with the negative value of k. This one I already told you. So we can say complementary root locus means is a root locus with a negative value of k. So what is the meaning of complementary root locus? Is a root locus with a negative value of k. That is called as a complementary root locus. Root locus means positive value of k. Complementary root locus means is a root locus with a negative value of k. The next point is adding of pole in the forward part transfer function increases the maximum overshoot, whereas adding a 0 reduces the maximum peak overshoot. So this one always you have to keep in your mind, which is adding of pole in the open loop transfer function increases the maximum overshoot, and adding a 0 reduces the maximum overshoot. So what I am trying to tell you, which is suppose if you are going to add a pole in the open loop transfer function, then what is going to happen? If you are going to add a pole to the forward part transfer function, we can say that the root locus is going to shift to RHS of S plane. The system is said to be unstable. And I have already told you, adding a pole means we can say it is a lag compensator. It is a lag compensator. So lag compensator is going to basically I have already told you, with the help of lag compensator, what is going to happen is going to improve the steady state response. Whereas adding a 0 means we can say it is going to shift the root locus to the RHS of S plane. So therefore the system is said to be stable. So we can say adding a 0 means we can say it's a lead compensator. Adding a pole means we can say it is a lag compensator. So this one I have already told you. So this one always you have to keep in your mind, which is adding of pole in the forward part transfer function increases the maximum overshoot, whereas adding a 0 reduces the maximum overshoot. This point always you have to keep in your mind. Now the next point is servo motors have the low inertia and a high starting torque, low rotor inertia, low wearing friction, small diameter and large action length. Servo motor has the low inertia, high starting torque, low bearing friction, small diameter and the large action length. I already told you basically for a servo motors which have the very high starting torque, as I already shown in the graph also. It has high starting torque, it has low inertia and also low bearing friction. It has small diameter by the large axle length, and X-bar ratio of the servo motor is always lesser when compared to X-bar ratio of the induction motor, normal induction motor. So X-bar ratio of the normal induction motor is higher than the X-bar ratio of the servo motor, because you can see the graph of the torque versus the speed for the normal induction motor is a very big size when compared to servo motor. So therefore we can say servo motors have the low inertia. It has low inertia means low weight. It has a high starting torque and also very small diameter but the very large action length. So now the next point is, which is, suppose V2 of S by V1 of S at a S is equal to 0 is equal to 0. Similarly, V2 of S by V1 of S at S is equal to infinity is again equal to 0. So V2 of S by V1 of S for any value of lies between 0 to infinity is not equal to 0, then we can say it is a band pass filter. Means for low frequencies its magnitude is equal to 0 and high frequencies its magnitude is equal to 0. But between these frequencies we can say this value is not equal to 0. So we can say it is a band pass filter. So we can say V2 of S by V1 of at S is equal to 0 is equal to 0. At S is equal to infinity also its value is equal to 0. But between 0 to infinity its value is not equal to 0. So therefore we can say it is said to be band pass filter. So if you draw the graph, we are going to get somewhat like this. So if you are going to draw the graph with respect to this S is equal to J omega, S is equal to 0 means omega is equal to 0. S is equal to infinity means omega is equal to infinity. So you are going to get like this. So this is called as a band pass filter. So band pass filter. This is equal to 0, this is also equal to 0. So only these frequencies are passed, so this is called a band pass filter. So now the next point is, a synchro transmitter consists of the silent pole rotor winding excited by a single phase AC supply and a three-phase balanced stator winding. A synchro transmitter consists of a silent pole rotor winding excited by a AC supply and a three-phase balanced stator winding. So what is a synchro transmitter? I have already told you. Synchro transmitter, basically the stator has three-phase winding and the rotor has single-phase winding. So this one I have already told you. So this is a single-phase winding and this is the three-phase winding for a synchro transmitter. I have already told you. In the case of synchro transmitter, the stator has the three-phase winding and the rotor has a single-phase winding. It is basically like a synchronous generator or synchronous motor. A synchro transmitter consists of a silent pole rotor winding excited by a single-phase supply and a three-phase balanced stator winding. So we can say a synchro transmitter, the stator has a three-phase winding and the rotor has a single-phase winding. It is basically like a synchronous motor or synchronous generator. So we can say simply like that. So a synchro transmitter consists of the silent pole rotor winding excited by an AC supply and a three-phase balanced stator winding. So we can say a synchro transmitter consists of the silent pole rotor winding excited by an AC supply and a three-phase balanced stator winding. So simply we can say for a synchro transmitter, the stator has a three-phase winding and the rotor has a single-phase winding. So this is the case always you have to keep in your mind. The next is, the torque speed characteristics of a two-phase induction motor is largely affected by the X-bar ratio. Yes, I already told you. The torque speed characteristics of a two-phase induction motor is largely affected by the X-bar ratio. Yes, the torque speed characteristics of the two-phase induction motor is largely affected by the X-bar ratio. And I have already told you, the X-bar ratio of the two-phase induction motor is always greater than the X-bar ratio of the servo motor. So this one I have already told you so many number of times. The X-bar ratio of the induction motor is always greater than the X-bar ratio of the servo motor. So whatever the torque speed characteristics of the two-phase induction motor, which are largely affected by the X-bar ratio. The next point is, phase lag compensator controller used for reduction in the steady state error. I have already told you, because phase lag controller is basically, lag compensator is basically used to improve the steady state characteristics, means it is going to reduce the steady state error. Whereas additional zero at origin used to improve the transient response. Then additional zero means we can say it is a PD compensator, because PD means derivative, means as terms you are going to get, zero terms you are going to get. So therefore addition of zero heterogeneous the lead compensator. So with the help of lead compensator, it is going to improve the transient response. So 1 by S means PI controller or lag compensator, whereas zero terms means we can say it is basically lead compensator, or it is going to improve the transient response. Derivative output compensation used to reduction in the settling time. So derivative output compensation used to reduction in the settling time. So with the help of derivative output compensation, basically it is used reduction in the settling time. So settling time decreases. Whenever you are going to use the derivative output compensation, the settling time is always going to get reduces. So we can say with the help of derivative output compensation, the settling time is always going to get reduces. So this point always you have to keep in your mind. So with the help of derivative output compensation, settling time is always going to get reduces. Derivative error compensation used to increasing in the damping constant. So listen carefully. Derivative output compensation means it is used to reduce the settling time, whereas derivative error compensation means it is used to increase the damping ratio, damping constant means beta increases. So these things always you have to keep in mind. So derivative output compensation is basically used to reduce the settling time, whereas the derivative error compensation is used to increase the damping ratio of damping constant. So these one always you have to keep in your mind. So simple words I can say, phase lag compensator is basically, or we can say lag compensator is basically used to improve the steady state response means the steady state error will decrease. Whereas phase period compensator means it is used to improve the transient response. Phase is also called as a PD controller means zero terms are going to get added. Then phase lag compensator means the two terms are going to get added, which is nothing but PI controller. So derivative output compensation is basically used to reduce the cycling time, whereas the derivative error compensation is basically used to increase the damping constant of damping ratio. The next point is the characteristics of the AC servo motor side. So now we'll discuss some characteristics of the AC servo motor, which are the torque speed curve as the negative slope. As I've already told you, whenever you are going to draw the graph between the torque versus the speed, so this is the speed and this is the torque. So we are going to it like this. So this is the speed increases, the torque is there. The torque increases. So therefore we can say this is nothing but negative slope. If one is increasing, the other is decreasing, means we can say negative slope. If both are increasing, means we can say positive slope. If one is increasing, the other is decreasing, means we say it is a negative slope. It is very less sensitive to noise. The servo motors are very less sensitive to noise. The rotor has high resistance and low inertia. So what I told you, XBR ratio is very less means high resistance, high rotor resistance. And it has low inertia means we can say small diameter and large axial length. It has high acceleration because the inertia is very less means the weight is very less. So definitely its acceleration will be very high. So we can say the characteristics of the AC servo motor are the torque itself. Torque speed curve has the negative slope, as you can see clearly from the picture. For the speed increases, the torque is decreases. If one increases, the other is decreasing, means it has a negative slope, and is very less sensitive to noise. So no matter what are the noise you try to impose, still the graph is same for all the time. And the XBR ratio of the servo motor is always very less, means the rotor has the high amount of resistance. So rotor has high resistance, and inertia is very less, means low weight. So therefore diameter is less and axial length is very more. So as it having a low weight, so it definitely will have high acceleration also. These are some of the points regarding the AC servo motor. The next point is, in the servo system, the gear backlash may cause sustained oscillations or chattering phenomena or low-level oscillations, and the system may even turn unstable for large bandwidth. In servo systems, the gear backlash may cause sustained oscillations or chattering phenomena or low-level oscillations, and the system may even turn unstable for large bandwidth. In servo systems, the gear backlash may cause sustained oscillations or chattering phenomena or low-level oscillations. So therefore, the system may even turn unstable for large bandwidth. So basically, in the case of servo systems, suppose if you are going to use the gear backlash, so because of this, some sustained oscillations are going to get present, which is also called as a chattering phenomena or low-level oscillations, which are going to present for all the time. So definitely, the system may even become unstable also for large amount of bandwidth. So therefore we can say, in the case of server system, if you are going to use the gain backlash, so because of this there will be some oscillations will be present for all the time, which can cause the chattering phenomena or low level oscillations which are present in the system for all the time, and it may even cause the unstable for large bandwidth. It may lead for the system to become unstable for larger bandwidth. So finally I can say, in the case of servo system, if you are going to use the gate backlash, it may cause the sustained oscillations or chattering phenomena or low level oscillations in the system for all the time, and it may cause the system to become unstable for even the larger bandwidth. So finally I can say, in the case of servo system, if you are going to use the gate backlash, then it may cause the some amount of sustained oscillations or chattering phenomena or low level oscillations which can be present in the system for all the time, and this may even turn the system to become unstable for large amount of bandwidth. The next point is, the transfer function of a lag grid compensator network is 1 plus S into T1A into 1 plus S into T2B by 1 plus S into T1 into 1 plus S into T2, where A is greater than 1, A is less than 1. So we can see clearly what are the zeros. Zeros are nothing but minus 1 by T1A and minus 1 by T2B. And what are the poles here? Poles are nothing but minus 1 by T1 and minus 1 by T2. So in the case of lag with compensator, first we are going to get the lag. Lag means you can say a pole 0. Then you are going to get the lead. 0 means 0, 1. So this is the, you can say, this is basically the lag. First you are going to get the, if you are going to move from this direction, first we are going to encounter the lag compensator, then the lead compensator. That is the reason it is called as a lag lead compensator. So here, this is nothing but pole we are going to get. So if you see clearly, out of these two poles, here you can see clearly, this is the, so you can see here A. Here A is greater than 1. A is greater than 1 means we can say that this value will be always lesser, very, very lesser. Means we can say this is minus 1 by T1A. Here, B is less than 1 means this value is very, very higher, very, very higher. So it will be minus 1 by T2B. So this will be minus 1 by T1 and this is minus 1 by T2. So these things we can easily see from this picture. This is the lag with compensator. So whenever you are going to move in this direction, first thing we are going to see the lag, then we are going to see the lead. In the case of lag, pole is near to origin when compared to 0. In the case of lead, 0 is closer to origin when compared to pole. So these things are only only so the number of times. The next one is a bridge T network is used for the cancellation compensation. So bridge T network is basically used for the cancellation compensation. So bridge T network is basically used for the cancellation compensation. Compensating network can be introduced in the feedback out of the control system. Compensating network can be introduced in the feedback path of the control system. So compensating network can be introduced in the feedback path of the control system. So compensating network can be introduced in the feedback path of the control system. So we can say compensating network can be introduced in the feedback path of the control system. So we can say compensating network can be introduced in the feedback path of a control system. So this point always you have to keep in your mind, which is the compensating network can be introduced in the feedback path of a control system. The compensating network can be introduced in the feedback path of a control system. Means in the case of feedback path also we can use the compensating network. The next point is the phase lag compensation improves the steady state response and often results in the increased rise time, means the speed of the time response is deteriorated to a certain extent. As I've already told you, phase lag compensation basically it is used to improve the steady state response. So definitely it is going to deviate the transient response. So we can say that phase lag compensation improves the steady state response and often is going to result in the increase in the rise time, means the speed of the rise time is deteriorated in a certain extent. So I've already told you, if it is going to improve one thing, means it is going to degrade the other thing. So this is a vice versa, very simple case. So I've already told you, phase lag compensation it is used to improve the transient response, means it is going to deteriorate the steady state response. Similarly to the phase lag compensator, it is used to improve the steady state response, means it is going to deteriorate the transient response. So deteriorating the transient response means the rest time will increase. So improving the steady state response means it is going to decrease the steady state error. So therefore we can say finally, the bridge tree network is basically used for cancellation, compensation. As a compensation network can be even introduced in the feedback of a control system. As a phase-like compensation, it is going to improve the steady state response and is often results in the increase in phase time means the speed of the current response is deteriorated to a certain extent. So this is the point always you have to keep in your mind. It is going to improve one thing means it is going to degrade the other thing. So this point always you have to keep in your mind. We can say some more points, which is input potentiometer in a DC system is basically it is used as a transducer, whereas the synchro pair in an AC system is basically used as the error detector, whereas the motor is basically used as the actuator, whereas a feedback type of generator is also used as a transducer. So what is the meaning of transducer? Transducer means if any physical quantity, if it is going to convert into electrical quantity, that is called as a transducer. So whenever you are going to change any physical parameter to electrical parameter, that is called as the transducer. So we can say if you are going to change any mechanical thing to electrical thing, that is the basic function of the transducer. So we can say input potentiometer in the DC system is basically used as the transducer because here input is the displacement and output is electrical voltage. So we can say it is a transducer because input is a displacement and the output is a voltage. So it is going to act like a transducer. Whereas a synchro pair in AC system is used as the error detector. It is going to act like a error detector. Whereas the motor is basically used as the actuator. Whereas the feedback type of generator is basically used as transducer. Here input is the mechanical motion and it means the rotational effect, speed of the shaft, and the output is the electrical voltage. So we can say it is a transducer. So therefore we can say the input potentiometer in the case of DC system is basically used as a transducer, whereas the synchro pair in the AC system is basically used as the error detector. Similarly, motor is used as the actuator, whereas the feedback type of generator is used as the transducer. I've already told you what is the meaning of transducer. Transducer is very simple. We are going to convert the physical parameter to electrical parameter, that is called as the transducer. So we can say in the case of potentiometer, the input is displacement and the output is electrical voltage. So it is used as a transducer. In the case of type generator also, input is we can say the rotational effect and the output is the voltage. So it is also used as a transducer. So finally I can say that input potentiometer in the case of DC system is basically used as the transducer, whereas the synchro pair in the AC system is also used as the error detector, whereas the motor is used as the actuator, whereas the feedback type of generator is also used as the transducer. The next point is servo motors normally have lower rotors and lower R/X ratio as compared to ordinary motors of similar ratings. Listen carefully. Servo motors normally have lower inertia, we can say lower rotor inertia and lower R/X. See, basically I've already told you X/R ratio of servo motor is lesser. So and lower R/X ratio also as compared to ordinary motors of similar ratings. So we can say so basically here let me write X/R, not R/X. I always used to tell you the X/R ratio. So therefore we can say small correction here. So I need to correct here. So therefore we can say servo motors have the low inertia as well as lower X/R when compared to any other ordinary motors of similar ratings. So whenever of similar ratings, if you compare any ordinary motor and servo motor, we can say servo motor having the lower inertia, lower rotor inertia as well as the lower X/R ratio. So these points always you have to keep in your mind. See, whenever you are going to compare two motors of similar ratings, one is of ordinary motor and the other is of servo motor, we can say servo motors have the lower rotor inertia and the lower X/R ratio. So these points always you have to keep in your mind. So whenever you are going to compare two motors of similar ratings, one is of the ordinary motor, the other is of servo motor. Servo motors will have the lower rotor inertia and lower X-bar ratio. So therefore we can say that servo motors normally have the lower rotor inertia and the lower X-bar ratio as compared to the ordinary motors of similar ratings. Yeah, the next point is servo motors should have smaller electrical and mechanical time constants for faster response. Servo motors should have the smaller electrical and mechanical time constants for faster response. Yes, the time constant is less, then only we can say the rise time is less. So therefore the response will be very, very faster. So whenever the electrical time constants as well as the mechanical time constants, if they are very, very smaller, then the rise time is very less. So therefore the speed of the response is very faster. So this is what we can easily say. So therefore we can say that whenever servo motors have the smaller as well as the electrical and mechanical time constants are smaller, we can say you are going to have the faster response. I already told you, for a servo motor, if you want a very faster response, then you should have the smaller time constants for electrical as well as the mechanical. So as the time constants are less, the rise time is also less. So therefore the speed of the response is very faster. So finally I can say that servo motors should have the smaller electrical and mechanical time constants to have the faster response. The next one is AC servo motors are essentially induction motor with a low X-bar ratio for the rotor, which has a very low inertia, drag cup type construction. So listen carefully. AC servo motors are essentially induction motor with a lower X-bar ratio for the rotor, which has very low inertia, drag cup type construction. I have already told you in the case of servo motor and the induction motor, X-bar ratio of the servo motor is always lesser than the X-bar ratio of the induction motor. And also, I have already told you, servo motors will have the low inertia, means lower weight, small diameter and the larger length. So basically its construction is the similar. The AC servo motor will have a construction in the format of drag cup type construction. So these point always you have to keep in your mind, which is AC servo motors are going to have the construction in the format of drag cup type construction. So these point always you have to keep in your mind, which is I can say finally in simple words I can say like this, which is AC servo motors are essential induction motors with a lower X-bar ratio for the rotor, which have a very low inertia. It has basically drag cup type construction. So in simple words I can say like this. In simple words, see AC servo motor. AC servo motors are basically it will have the lower X-bar ratio when compared to induction motor. And also they have low inertia, so therefore low weight. So the diameter is very lesser and the length is very, very larger. So this construction is in the format of the drag cup type construction. The next concept is the next point is the phase-lag converter is a low-pass filter. I have already told you so many number of times how to remember the shortcut. So here it is a lead, here it is a lag. So lead has more volts, so transient also has the more volts. Transient. As a lag has less volts, so steady also has less volts. So therefore we can say match two things of more volts, match two things of less volts. So lead comparison is basically used to improve only the transient response. So it is going to degrade the steady state response. Whereas lag comparison is used to improve the steady state response. So it is going to degrade the transient response. If it is going to improve one means it is going to degrade the other thing. So this you have to keep in your mind. So lead capacitor means zero comes earlier than pole. So 0 is going to come earlier than pole means we are going to get initially plus 2 decibels per decade. Then again minus 1 means plus 1 minus 1 0 decibels per decade. So we can say plus 20 decibels per decade and 0 decibels per decade means it is a high pass filter. So this is nothing but high pass filter. Whereas here in lag capacitor, pole is going to come earlier than 0. So pole is very closer to origin and compared to 0. So therefore initially you are going to get minus 20 decibels per decade. Then 0 which is plus 20 decibels per decade means we are going to get finally the overall whatever I have to plot will have slopes like it is minus 20 decibels per decade and 0 decibels per decade. It indicates that it is a low pass filter. So therefore we can say this is the low pass filter. So same thing I have already told you. Phase lag capacitor is a low pass filter whereas the lead phase 3 compressor is a high pass filter, as you can see clearly from this picture. The next one is the correct reasons to select the feedback compensation over the cascade one. So what are the correct reasons in order to select the feedback compensation over the cascade one? See, no amplification is required as the energy transfer is from higher level to lower level, whereas the suitable devices are not available for compensation series. It is going to provide the greater stiffness against the low disturbances, and cascade compensation is quite satisfactory and economical in most cases compared with the feedback compensation. So now we are going to see clearly this facts, which is the correct reasons to select the feedback compensation over the cascade one. So we are going to tell you some basic reasons in order to select the feedback compensation over the cascade one. Why we are going to prefer the feedback compensation over the cascade compensation. Why it is like this? Which is, no amplification is required as the energy transfer is taken place from higher level to lower level. So no amplification is required because the energy transfer is always from the higher level to lower level. And the suitable devices are not available for compensation series. So basically there are no suitable devices which are, basically the suitable devices are not available for the cascade compensation, or we can say series compensation. So it is going to provide the greater stiffness against the load disturbances. So with the help of feedback compensation, it is going to provide the greater stiffness even against any load disturbances. Whereas the cascade compensation is quite satisfactory as well as economical in most cases compared with the feedback compensation. So cascade compensation is quite satisfactory as well as economical in most cases is compared with the feedback compensation. So we can say that the correct reasons, the proper reasons that we are going to prefer the feedback compensation over the series compensation or cascade compensation, which is no amplification is required as the energy level is always taking place from the higher level to lower level in the case of feedback compensation. And also there are no suitable devices which are available for the series compensation or the cascade compensation, and we can say that the feedback compensation is going to provide the greater stiffness against any load disturbances, whereas the cascade compensation is quite satisfactory and economical in most cases when compared with the feedback compensation. So these are some of the reasons in order to prefer the feedback compensation over the cascade compensation. So finally I can say the correct reasons in order to select the feedback compensation over the cascade compensation or series compensation, which is no amplification is required as the energy transfer is always taking place from higher level to lower level in the case of feedback compensation, and there are no suitable devices which are available for the series compensation or the cascade compensation. And we can say that the feedback compensation is going to provide the greater stiffness against any load disturbances, whereas the cascade compensation or the series compensation is quite satisfactory and also economical in most cases when compared with the feedback compensation. So these are the important reasons in order to select the feedback compensation over the cascade compensation. Now the next point is, amplidiode is used as the servo amplifier, whereas the potentiometer is used as the error detector, whereas the stepper motor is used as the actuator, whereas the AC taper generator is used as the rate feedback. So listen carefully. Amplidiode is basically used as the servo amplifier. Potentiometer is used as the error detector. It is also used as the transducer. I've already told you. But in a specific application, it can be also used as the error detector. Whereas the stepper motor is basically, it is used as the actuator, whereas the AC taper generator is used as the rate feedback. Or you can also call it is also used as the transducer also, we can easily say. So we can say finally, amplidiode is used as the servo amplifier, whereas the potentiometer is used as the error detector, whereas the stepper motor is used as the actuator, whereas the AC taper generator is used as the rate feedback. So listen carefully. Amplidiode is basically used as the servo amplifier, whereas the potentiometer is used as the error detector, whereas the stepper motor is used as the actuator, whereas the AC taco generator is basically used as the rate feedback. So this point always you have to keep in your mind. So for a given specific application, we can say amplidian is basically used as a servo amplifier, whereas the potentiometer is basically used as the error detector, whereas the stepper motor is used as the actuator, whereas the AC taco generator is used as the rate feedback. So finally I can say for a given specific application, we can say amplidian is basically used as a servo amplifier, whereas the potentiometer is used as the error detector, whereas the stepper motor is used as the actuator, whereas the AC taco generator is used as the rate feedback. So finally, I can say amplidian is basically used as the servo amplifier, potentiometer is used as the error detector, stepper motor is used as the actuator, whereas the AC taco generator is used as the rate feedback. So finally, I can say for a given specific application, amplidian is used as the servo amplifier, potentiometer is used as the error detector, stepper motor is used as the actuator, AC taco generator is used as the rate feedback. So finally, I can say the next point is a linear AC servo motor has the lower X/R ratio to make the torque slip characteristics to be linear. As I already told you, I have already drawn the graph between the torque versus speed or torque versus slip. You can call it anything. So torque versus speed. Let me draw the graph. So I have already told this concept, but let me draw this one. So this is the torque speed characteristics of the servo motor, whereas the torque, if you consider the torque speed characteristics of the two-phase induction motor is like this one. So this is for the two-phase induction motor, and this is for the servo motor, as you can see clearly from this picture also. So this is for the servo motor. So you can see clearly the X/R ratio of the servo motor is always lesser than the X/R ratio of the induction motor. So because of this reason only, we are going to get a linear torque speed characteristics for the servo motor. So because X/R ratio is very lesser, that is the reason we are going to get a linear characteristics of the torque speed and torque slip. So we can say the linear AC servo motor has the lower X/R ratio in order to make the torque slip characteristics to be linear. So we can say finally a linear AC servo motor has the lower X/R ratio in order to make the torque slip characteristics to be linear. So we can say a linear AC servo motor has the lower X/R ratio in order to make the torque slip characteristics to be linear. So finally I can say a linear AC servo motor has the lower X/R ratio in order to make the torque speed or torque speed characteristics to be linear. So finally I can say a linear AC servo motor has the lower X/R ratio in order to make the torque slip characteristics to be linear. The next point is amplidian is used as the control amplifier, whereas the potentiometer is used as the error detector, whereas the stepper motor is used as the actuator, whereas the AC taco generator is used as the feedback element. Listen carefully. Amplidian is used as the servo amplifier or control amplifier, whereas the potentiometer is used as the error detector, whereas the stepper motor is used as the actuator, whereas the AC taco generator is used as the rate feedback or feedback element. Just now we have discussed this one. So we can say amplidian is used as a servo amplifier or control amplifier, whereas the potentiometer is used as the error detector, whereas the stepper motor is used as the actuator, whereas the AC taco generator is used as the rate feedback or feedback element. So finally I can say amplidian is basically used as the control amplifier or servo amplifier. Potentiometer is used as the error detector, whereas the stepper motor is used as the actuator, whereas the AC taco generator is used as the rate feedback or the feedback element. So finally I can say amplidian is basically used as the control amplifier or servo amplifier, whereas the potentiometer is used as the error detector, whereas the stepper motor is used as the actuator, whereas the AC taco generator is used as the feedback element. So finally I can say amplidian is basically used as the servo amplifier or control amplifier, As a potentiometer is basically used as the error detector, whereas the stepper motor is basically used as the actuator, whereas the AC tacho generator is used as the rate feedback or feedback element. The next point is, in a speed control system, the output rate feedback is used to limit the speed of the motor. Yes, in the case of speed control system, the output rate feedback is basically used to limit the speed of the motor, because with the help of output rate feedback, we are going to give the feedback of output to the input. So based on this, we are with the help of some controller, we are going to control the speed of the motor, or we are going to limit the speed of the motor. That is the basic function of the feedback, rate feedback. So therefore, we can say in a speed control system, the output rate feedback is basically used to limit the speed of the motor. So we can say that in the case of the speed control system, the output rate feedback is basically used to limit the speed of the motor. So we can say in the case of speed control system, the output rate feedback is basically used to limit the speed of the motor. So we can say in a speed control system, the output rate feedback is basically used to limit the speed of the motor. So in simple words, I can say basically, suppose with the help of rate feedback, we are going to give the feedback of output to input. So based on this, then the controller is going to control the speed of the motor, or we can say it is going to limit the speed of the motor. So finally, I can say in the case of speed control system, the output rate feedback is basically used to limit the speed of the motor. The next point is, in the case of lag lead compensators, a lag and a lead compensators are basically connected in series. Yes, in the case of lag lead compensators, a lag and a lead compensator are basically connected in series. I've already told you this in a very detailed fashion. Also, I've already told you lead compensator, lag compensator, and lag lead compensator. See, whenever you are going to combine the lag compensator and lead compensator in series, then we are going to get the overall lag lead compensator. So whenever you are going to combine the lag compensator and the lead compensator in series, then overall you are going to get the lag lead compensator. So we can say finally, in the case of lag lead compensator, a lag and a lead compensator are basically connected in series. The next point is, the AC plane representation of the lead compensation as a zero closer to origin than the pole. See, I have already told you in the case of lead compensator, the zero is closer to origin when compared to pole. Whereas in the case of lag compensator, the pole is closer to origin than the zero. So this one I have already told you so many number of times. And the lead compensator is basically used to compensate. See, I have already told you the lead compensator is basically used to improve the transient response. So it is going to deviate the steady state response. As the lag compensator is basically used to improve the steady state response. So it is going to deviate the transient response. So in the case of lead compensator, zero is closer to origin. Zero is closer to origin than a pole. Whereas in the case of the phase lag compensator, pole is closer to origin than the zero. So we can say that I have already told you the lead compensator is also called as a high pass filter, whereas the lag compensator is also called as the low pass filter. So this one I have already told you so many number of times. The next point is, we can say, what is the next point now? The next point is very simple. You can see clearly that a lag compensator improves the steady state behavior of a system while nearly maintaining its transient response. So same thing here, you can say a lag compensator is going to improve the steady state behavior of the system while nearly maintaining its transient response. While nearly it is going to maintain its transient response, but it is going to deviate to a smaller extent. But we can say it is nearly maintaining its transient response, but if you speak frankly, it is going to deviate to a smaller extent, but not more, but to a smaller extent. So we can say a lag compensator is basically, it is going to improve the steady state behavior of the system while nearly maintaining its transient response. So we can say a lag compensator improves the steady state behavior of the system while nearly maintaining its transient response. So in simple words, I can say like this: a lag compensator improves the steady state behavior of a system while nearly maintaining its transient response. But if you speak frankly, I have already told you, a lag compensator is going to improve the steady state behavior of a system while nearly deviating. It is going to deviate There is a response for an extent, but if you speak in terms of approximation, clearly it is going to maintain its transient response. So always remember, any compensator, if it is going to improve other things, it is going to degrade the other thing to a smaller extent. So these will always have to keep in your mind. The next point is the transfer function of a lag network, which is k into 1 plus ATS by 1 plus TS. Then what is the value of A? So you can see what is the 0 here? 0. What is the 0 here? You can see 0 is equal to minus 1 by AT. And what is the value of pole? Pole is equal to minus 1 by 3. In the case of lag compensator, the pole is closer to origin than a 0. So we should be very closer to origin based compared to units. What is the value of A? A should be lesser than 1. Then only we can see it is very, so less means overall value will be very, so you can say it will be very far away. So 0 is, you can say A value is lesser than 1 here. So generally, the pole is closer to origin when compared to 0. So this is called a lag compensator. The next one is the transfer function of a servo motor, which is Km by S into 1 plus S to U. So I've already told you what is the transfer function of a servo motor. We have already discussed, which is Km by S into 1 plus S to M. So this one I've already told you so many times. So we can say finally, for a servo motor, its type is 1. Its type is 1. Type of system is 1. So the order of the system is 2. So you can see clearly from there, its type of the system is 1, whereas the order of the system is 2. As you can see clearly from this transfer function. So for a servo motor, its type is equal to 1 and the order is equal to 2. So this is the transfer function of AC servo motor, which is Km by S into 1 plus S to M. So type of the system is 1 and order of the system is 2. Whereas the transfer function of the field control DC servo motor. So what is the transfer function of field control DC servo motor? Field control means we are going to vary the field supply voltage in order to control the speed of the motor. And what is the transfer function that we are going to be K by S into 1 plus S 2M into 1 plus S 21. So you can see the type of system is 1 and order of the system is 3. This one I have already told you in my concepts class also. So we can say finally the transfer function of lag network of lag compensator, which is we can say that K into 1 plus ATS by 1 plus TS, and the value of A is lesser than 1. Whereas the transfer function of A servo motor, which is Km by S into 1 plus S to M. Whereas the transfer function of field control DC servo motor, which is K by S into 1 plus S to M into 1 plus S to 1. Whereas the transfer function of the TACO generator. TACO generator means I already told you TACO generator. So I already told you what's TACO generator. Your output is voltage and input is speed. So output is directly proportional to rate of change of speed. So if you do the Laplace transform, we are going to get E naught of S is equal to S into, it may assume sometimes K, constant K into omega of S. So the transfer function E naught of S by omega of S is K into S. So this is the transfer function. Same thing we can see here, the transfer function of TACO generator, which is equal to K1 into S. So this you can see here, because the TACO generator, the output is at proportional to rate of change of speed. So here is at proportional to d omega by dt. So if we give the proportional to constant, we are going to get some constant K. So with the Laplace transform on both sides, we are going to get E naught of S is equal to K into S into omega of S. So transfer function is E naught of S by omega of S, which is equal to K into S. K into S is the transfer function. So these things always you have to keep in your mind. So therefore finally I can say the transfer function of the lag network, which is K into 1 plus ATS by 1 plus TS, with the value of A is lesser than 1, and the transfer function of A servo motor, which is Km by S into 1 plus S to M, is the transfer function of the field control DC servo motor, which is K by S into 1 plus S to M into 1 plus S to 1, and the transfer function of TACO generator, which is K1 into S. So these things always you have to keep in your mind. The next point is, these servo motors are more commonly used in the armature control mode instead of in the field control mode, because armature control DC motors have the higher starting torque than the field control motors. So listen carefully. These servo motors are more commonly used in the case of armature control mode instead of the field control mode, because armature control DC motors have the higher starting torque than the field control motors. To get higher speed in field control DC motor, field current is decreased which is going to decrease the torque. So listen carefully. What I am going to do, I have already told you armature control DC motors and the field control DC motors. So whenever we are going to compare the armature control DC motors as well as the field control DC motors, we are going to get the higher starting torque only in the case of the, so always we are going to get the higher starting torque only in the case of armature control DC motors. So why it is like this? Because in the case of field control, if you want the higher speed, definitely you have to decrease the field current. So as the field current decreases, field flux decreases, so higher speed you are going to get, the torque is also going to get decreases. So listen carefully, here I am going to write some important point. So this is basically armature control DC servo motor, armature control DC motors, and the field control DC motors. So here the start torque is equal to high, whereas here the start torque is equal to low. So in the case of armature control, the speed is lesser than the rated speed, and the speed is greater than the rated speed. So I already told you, so here as the speed is greater than rated speed, so definitely the field current should decrease. So field flux decreases, so speed will increase. So as the field current decreases, the torque is also going to get decreases. So therefore, the start torque is equal to low in this case. And in the case of armature control DC motors, here the start torque is high because the speed is lesser than the rated speed. So we can say DC servo motors are more commonly used in the case of armature control mode instead of in the case of field control mode, because armature control DC motors have higher starting torque than the field control motors. To get higher speed in the field control DC motor, field current is decreased, which is going to decrease the torque. So in order to get the higher speed in the case of the field control DC motor, field current is decreases, so it's going to decrease the torque. So in simple words I can say, so I already told the armature control DC motor and field control DC motor. In the case of armature control DC motor, the start torque is always high, whereas in the case of field control DC motor, the start torque is always less. Because in the case of armature control DC servo motor, here the speed is lesser than rated speed. But in the case of field control DC motor, here the speed is greater than rated speed. As the speed is greater than rated speed, so you need less amount of flux. Less amount of flux is possible with less amount of rated current. So therefore, the torque is proportional to flux into armature current. So as the flux decreases, torque is also going to get decreases. So you can say the start torque is lesser in the case of field control motor. So these servo motors are basically commonly used only in the case of armature control mode instead of in the field control mode, because armature control DC motors having the higher starting torque than the field control motors. In order to get the higher speed in field control DC motor, field current is decreases, so therefore it is going to decrease the torque in the case of field control DC motor. The next point is, with the lag here compensation, the bandwidth of the system is not affected much because the effect of lag and lead compensators at higher frequencies cancel one another. With the lag lead compensation, the bandwidth of the system is not affected much because the effect of lag and lead compensators at higher frequencies cancel one another. So basically, suppose there is a control system. For this control system, initially also the bandwidth is we can say the bandwidth is we can say it is equal to some x. So now we are going to introduce the lag compensation into this control system. So even though the bandwidth is not going to vary that much, it will remain as same as the previous one. So because at higher frequencies, both this lag and lead are going to get cancelled each other. So therefore, the bandwidth is going to remain same as it is. So we can say with lag lead compensation, the bandwidth of the system is not affected much because the effect of the lag and the lead compensators at higher frequencies, they are going to cancel one another. So we can say with the lag lead compensation, the bandwidth of the system is not affected much because the effect of lag and lead compensators at higher frequencies, they are going to cancel one another. So in simple words, I can say like this. Suppose for some control system, it is having some bandwidth, some x. So now we are going to introduce this lag lead compensator in this control system. Still, the bandwidth of the system is same as the previous case because here at higher frequencies, both this lag compensator and the lead compensator effects are going to cancel. So therefore, the bandwidth will remain same as it is. So we can say finally, with lagged compensation, the bandwidth of the system is not affected much because the effect of the lag and the lead compensators at higher frequencies, they are going to cancel one another. The next point is, you can see clearly here that the effect of tachometer feedback in a control system is to reduce only gain. The effect of tachometer feedback in a control system is basically used to reduce only the gain. So we can say tachometer feedback is we are going to use some feedback. Feedback supplement, this is basically a negative feedback. So negative feedback means definitely we can say the gain is going to get decreases. So therefore we can say the effect of tachometer feedback in a control system is mainly it is used to reduce only the gain. So finally I can say that whenever you are going to use a tachometer feedback means it's a negative feedback. So with the help of negative feedback, the gain of the system is going to get reduces. So therefore we can say the effect of tachometer feedback in the control system is to reduce only the gain. So finally I can say the effect of tachometer feedback in the control system is basically it is used to reduce only the gain. So finally I can say the effect of tachometer feedback in a control system is basically it is used to reduce only the gain. The next point is tacho-generator feedback is used as a minor loop feedback in position control systems in order to improve the stability. So this is a very important statement. The tacho-generator feedback is basically it is used as a minor loop feedback in the case of position control systems in order to improve the stability. So why we are going to use a tacho-generator feedback in order to control the speed of the system. So therefore, it is basically used to improve the stability because I already told it's a negative feedback system. So tacho-generator means basically we are going to use a negative feedback system in order to improve the stability. So therefore, we can say that tacho-generator feedback is basically it is used as a minor loop feedback in the case of position control systems in order to improve the stability. Minor loop means so outside that also there is also bigger loop. So there is a smaller loop and there is outside it that one there is also a bigger loop. That is the result is called as a minor loop feedback. So we can say tacho-generator feedback is basically used as the minor loop feedback in the position control systems in order to improve the stability. So we can say tacho-generator feedback is basically used as the minor loop feedback in the case of position control systems in order to improve the stability. So finally I can say that tacho-generator feedback is basically it is used as the minor loop feedback in the position control systems in order to improve the stability. The next point is tacho-generator provides velocity feedback which is going to reduce as the only gain in the system. Tacho-generator provides velocity feedback which is going to decrease the only gain in the system. I've already told you tacho-generator means the output one is either proportional to the rate of change of speed. So therefore, we can say that it is going to give the input as a rate of change of velocity and output we are going to get the voltage. So with the help of this tacho-generator. So basically, we can say it is going to provide the velocity feedback. It is nothing but negative feedback system. So overall gain is going to get reduces. So we can say if this tacho-generator is basically it is a velocity feedback or negative feedback. So with the help of this, the gain is going to get decreases. It is a minor loop feedback in the case of over a total. It's a minor loop feedback in the case of position control systems. And with the help of negative feedback, we are going to improve the stability. So finally, I can say this tacho-generator is going to provide the velocity feedback, which is going to decrease the only gain of the system because the negative feedback. So with the help of this, the gain is going to decreases, but the stability is going to get increases. The next point is gyroscope. Gyroscope is basically it is used for measuring. Is basically used for measuring inclination of frames in the inertial navigation system. Whereas a stepper motor is used as the actuator element in the case of the computer printer. Whereas a servo motor is basically it is used for the low power applications. So we can say that the gyroscope is basically it is used for measuring the inclination of the frames in the case of inertial navigation system. Whereas the stepper motor is basically used as an actuator element in the case of computer printers. Whereas the servo motors is used as the it is used for low power applications. So we can say that gyroscope is basically used for measuring the inclination of frames in the case of inertial navigation system, whereas a stepper motor is basically it is used as an actuated element in the case of computer printer, whereas a servo motor is basically used for the low power applications. So listen carefully that gyroscope is basically used for measuring the inclination of the frames in the inertial navigation system, whereas the stepper motor is basically it is used as an actuated element in the case of computer printer, whereas the servo motor is basically used for the low power applications. So finally, I can say that gyroscope is basically it is used for measuring the inclination of the frames in the inertial navigation system, whereas the stepper motor is basically it is used as an actuated element in the case of computer printer, whereas the servo motor is basically used for low power applications. I've already told you basically the servo motor is basically used only for the low power applications because it is going to have the low expiry ratios. So therefore it has a low inertia, it has a small diameter but large length. So we can say finally that the gyroscope is basically it is used for measuring the inclination of the frames in the case of inertial navigation system, whereas the stepper motor is used as an actuated element in the case of computer drive, and servo motor is basically used for the low power applications. So these one always you have to keep in your mind. So we can say that the gyroscope is basically it is used for measuring the inclination of the frames in the case of inertial navigation system, whereas the stepper motor is used as an actuated element in the computer printer, whereas the servo motor is basically used for the low power applications. So in simple words, I can say gyroscope is basically it is used for measuring the inclination of the frames in the case of inertial navigation system, and the stepper motor is basically it is used as an actuated element in a computer printer. Actuated element means it is going to move the computer print above and below, downward. Whereas servo motor is basically used for low power applications. So finally, I can say gyroscope is basically used for measuring the inclination of frames in the case of inertial navigation system, whereas the stepper motor is used as the actuated element in the case of computer printer. It is going to move the computer printer, the frame upward and downward. It is called the actuated element. Whereas servo motor is basically used only for the low power applications only, because it is going to have the low expiry ratio when compared to two-wheel induction motor. It has a lower rotor inertia, it has small diameter but large axial length. So this one I already told you so many number of times. The next point is synchronous is basically used as the error detector, whereas the operation amplifier is used as a controller, whereas the stepper motor is used as the actuator, whereas the tacho generator is basically used as a feedback element. Same thing here. See, basically each and every element, what is the applications which are going to use in the case of control system. Synchronous is basically used as the error detector, whereas the operation amplifier it is used as a controller, because here for operation amplifier you will get a positive and there is a negative, inverted terminal and non-inverted terminal. So based on this, it is going to give some output. So it is used as a basically a controller. And the stepper motor means we can say it is basically it is going to, in the case of computer printer, it is going to move the parts. So this basically it is called as the actuator. For the tacho generator, it is basically used as a feedback element in order to control the speed of the motor. So we can say finally you can say synchronous is basically used as an error detector, whereas the operation amplifier is basically it is used as the controller, whereas the stepper motor it has basically it is used as an actuator, whereas tacho generator is basically used as a feedback element. So finally I can say synchronous is basically it is used as the error detector, whereas the operation amplifier is used as the controller, whereas the stepper motor is basically used as the actuator, whereas the tacho generator is basically used as a feedback element. So finally I can say the synchronous is basically used as the error detector, whereas the operation amplifier it is used as a controller, whereas the stepper motor it is used as the actuator, whereas the tacho generator it is used as the feedback element. So finally I can say synchronous is basically it is used as the error detector, whereas the operation amplifier it is used as a controller, whereas the stepper motor it is used as the actuator, whereas the tacho generator it is basically used as the feedback element. So finally, I can say synchros is basically it is used as the error detector. There is an operation amplifier which is used as the controller, or the stepper motor which is basically used as the actuator, whereas the taco generator which is basically used as the feedback element. So finally, I can say synchros is basically it is used as the error detector. As the operation amplifier is used as a controller, as a stepper motor it is used as an actuator, whereas the taco generator it is basically used as the feedback element. The next point is a linearized torque speed curve is required for stability in the case of a AC servo motor. So a linearized torque speed curve is required for stability of an AC servo motor. So basically I have already told you the torque speed characteristics of a AC servo motor will be in the fashion of linear. So therefore it is because of the X-bar ratio is very less. So a linearized torque speed curve is required in case of the stability of an AC servo motor. So we can say a linearized torque speed curve is required for stability in the case of the AC servo motor. So we can say a linearized torque speed curve is required for stability in the case of the AC servo motor. Or we can say a linear torque speed curve is required in the case of AC servo motor for being stable because its X-bar ratio is very lesser. So because of this we can say it is having a very linearized torque speed curve. So a linearized torque speed curve is required for stability of an AC servo motor. So we can say a linearized torque speed curve is required for stability of an AC servo motor. So we can say a linearized torque speed curve is required for stability of an AC servo motor. So a linearized torque speed curve is required for stability of an AC servo motor. So finally I can say a linearized torque speed curve is required for stability of an AC servo motor. The next point is microsim is based on the principle of rotating differential transformer. So microsim is based on the principle of rotating differential transformer. So this microsim is basically works on the principle of the rotating differential transformer. So we can say this microsim is basically works on the principle of the rotating differential transformer. So this microsim basically works on the principle of the rotating differential transformer. So this microsim is basically it is going to work on the principle of the rotating differential transformer. So this microsim is basically works on the principle of the rotating differential transformer. So this microsim is basically it works on the principle of the rotating differential transformer. So we can say this microsim is basically works on the principle of the rotating differential transformer. So this microsim is basically works on the principle of the rotating differential transformer. The next point is the effect of providing distance velocity lag or transportation lag is to reduce the phase margin. The effect of providing distance velocity lag or transportation lag is to basically to reduce the phase margin. So we can say the effect of providing distance velocity lag or transportation lag is basically to reduce the phase margin. So we can say the effect of providing distance velocity lag or transportation lag is basically to reduce the phase margin. So the effect of providing distance velocity lag or transportation lag is basically used to reduce the phase margin. So we can say the basic agenda or the basic aim of using the transportation lag. What is the meaning of transportation lag? The output is going to lag the input by some amount of time. So why we are going to use like this? Because in order to reduce the phase margin. So transportation lag means the output is going to lag the input by some amount of time. So why we are going to make this one? Why we are going to use this transportation lag? Because we want to reduce the phase margin. The effect of providing distance velocity lag or transportation lag is basically to reduce the phase margin. The effect of providing distance velocity lag or transportation lag is basically used to reduce the phase margin. So we can say the effect of providing distance velocity lag or transportation lag is to basically to reduce the phase margin. In simple words, I can say like this, which is transportation lag means the output is going to lag the input by some amount of time. So why we are going to introduce this one in the system? Because we want to reduce the phase margin. So finally I can say The effect of providing distance velocity lag or transmission lag is to basically reduce the phase margin. The next point is by using lag compensator. I've already told you lag compensator is basically used to improve the steady state response. So it is going to degrade the transient response to some amount of time. So then what is going to happen? The rise time is going to get increases. So I've already told the rise time is going to get increases. So bandwidth will decrease because both are inversely proportional, or you can say that rise time to bandwidth is always equal to constant. As rise time increases, the bandwidth must decrease. And the signal to noise ratio is going to get improved. Why it is like this? Only in the case of lead compensator, there is a differentiator. So therefore, the noise is going to get increases. Whereas here in the phase lag, there is no differentiator. So therefore, the noise is going to get decreases. So signal to noise ratio is going to get increases or it is improved. So therefore, we can say finally, with the help of lag compensator is basically it is used to improve the steady state response, but it is going to degrade the transient response to a smaller extent. So therefore, the rise time increases, so speed of response is very less. So as the rise time increases, bandwidth decreases because the velocity is always equal to constant. And here there is no differentiator, so definitely the noise is very less. So signal to noise ratio is going to get improved or it is going to get increases. So now the next point is by using phase theory compensator. So by using phase theory compensator, I've already told you with the help of lead compensator, the transient response is going to get improved, but the steady state response is going to get degraded to a smaller extent. So therefore, we can say as we are going to improve the transient response, so therefore the rise time decreases. So as the rise time decreases, the bandwidth increases because the product is always equal to constant. And I've already told you in all the three cases, the damping ratio is always going to get increases. Whereas in the phase 3 or the phase lag, the damping ratio is always going to get increases. So therefore, the P portion decreases because both are inversely proportional. The next point is the characteristics of the phase shift compensation is when used properly, it can increase the damping of the system. It improves. So you can say the characteristics of the phase shift compensation is when used properly, it can increase the damping of system as theta increases. It is going to improve the rise time. It improves the rise time. The rise time is going to get decreased. It is going to improve rise time. It is going to decrease the rise time. So bandwidth will increase. I have already told you as the damping ratio increases, the P portion will decreases. The rise time is decreases. So you can say damping ratio is going to get increases. It improves the section time. Improves means the section time is going to get decreased. It does not affect the steady state error. So it is not going to affect the steady state error. So these things always you have to keep in your mind in the case of phase shift compensation. So what is going to happen in the case of phase shift compensation? So with the help of phase shift compensation, it is going to improve the transient response. But it is not. But we can say practically, it is going to degrade the steady state response to a smaller extent only. So we can say here, it is going to improve the rise time is going to get decreases because it is going to improve the speed of the response. As the rise time decreases, the bandwidth will increase. I have already told in all the three cases, the damping ratio is going to get increases. So therefore, the P portion will decrease because both are inversely proportional. And I have already told you, the noise is going to get improved because of the differentiator. P means differentiator. So as noise increases, so signal to noise ratio is going to get degraded, or it is going to get decreases. Cycle time is also going to get decreases. Cycle time is also going to get decreases. Cycle time is also going to get decreases. Means we are going to get the faster response. See, basically, the speed of the response is very fast. Means the cycle time is going to get decreases. So generally, you are going to get the response very faster. So as the cycle time is decreases, we are going to get the response very faster. That is a basic agenda of this one. It is going to improve the speed of the response. Means the cycle time will decreases. But it is not going to affect the steady state error. So the next point is to detect the position errors in the position control system. The following are used: either the potentiometers, or whether it is a synchronous or is a linear variable differential transformer. So in order to detect the position errors in the case of position control systems, the following are used: whether it is a potentiometers, synchronous or LVDT. So we can say, in order to detect the position errors in the case of position control systems, The following are used, which is the potentiometers or synchros or LVDT. So we can say, in order to detect the position errors in the case of position control systems, the following are used, whether it is the potentiometers or synchros or LVDT. So we can say, in order to detect the position errors in the case of position control systems, the following are used, which is the potentiometers or synchros or LVDT. So in simple words, I can say the potentiometers, the synchros and the LVDT, which are basically used for the for calculation of the position errors in the case of position control systems. So we can say these potentiometers, synchros and LVDT, they are basically used to detect the position errors in the case of position control systems. So we can say that these potentiometers, synchros as well as the LVDT, they are basically used to detect the position errors in the case of the position control system. So these potentiometers, synchros and LVDT, they are basically used to detect the position errors in the case of position control system. So we can say that these potentiometers, synchros and LVDT, they are basically used to detect the position errors in the case of position control systems. So we can say these potentiometers, synchros and LVDT, they are basically used to detect the position errors in the case of the position control system. So finally I can say these potentiometers, synchros and LVDT, they are basically used to detect the position errors in the case of the position control system. So we can say that this one, which is basically, you can say these potentiometers, synchros as well as LVDT, they are basically used to detect the position errors in the case of position control system. So we can say these potentiometers, these synchros and LVDT, they are basically used to detect the position errors in the case of the position control system. So finally I can say the potentiometers, the synchros, LVDT, these are basically used to detect the position errors in the case of position control systems. The next point is a tachometer is added to a servo mechanism in order to convert the velocity of the shaft to a proportional to DC voltage. I already told you, tachometer means it is going to convert the speed into voltage, because I already told you the output is as proportional to the rate of change of velocity. So therefore, we can say a tachometer output is a voltage and input is the mechanical speed. So tachometer is basically added to a servo mechanism in order to convert the velocity of the shaft to direct DC voltage. So what are the DC voltage is nothing but is a DC voltage. So DC polarity voltage. So we can say a tachometer is basically added to a servo mechanism in order to convert the velocity of the shaft to a proportional DC voltage. So we can say a tachometer is basically added to a servo mechanism in order to convert the velocity of the shaft to a proportional DC voltage. So we can say a tachometer is added to a servo mechanism in order to convert the velocity of the shaft to a proportional DC voltage. So we can say basically this tachometer is basically added to a servo mechanism in order to convert the shaft velocity into a proportional DC voltage, because the input is a mechanical velocity and output we are going to get a DC voltage. That is a basic agenda of the tachometer. So finally I can say the tachometer is basically added to a servo mechanism in order to convert the velocity of the shaft to a proportional DC voltage. So these things always you have to keep in your mind.